Nutella, Jif peanut butter, and Hershey syrup are three spreads that dominate kitchens around the world. Each one begins with simple raw ingredients that are roasted and refined through massive industrial systems to create smooth and creamy textures. In this video, we uncover how hazelnuts, peanuts, and cocoa are transformed step by step into the iconic spreads and syrups that fill jars and bottles by the millions every day. Nutella's key ingredients are hazelnuts, sugar, palm oil, cocoa solids, skimmed milk powder, whey powder, lecithin as an emulsifier, and vanillin as a flavoring agent. Each of these ingredients is sourced globally, selected for consistency, taste, and availability. Hazelnuts, the signature ingredient, are predominantly sourced from Turkey, which produces more than 2/3 of the world's supply. However, Italy, Chile, and the United States also contribute to the global hazelnut harvest. Ferrero, the company behind Nutella, maintains long-term relationships with growers and has implemented traceability programs to ensure that hazelnuts meet quality standards for moisture content, size, and taste. Upon arrival at the processing facility, hazelnuts go through rigorous inspection and sorting procedures. This is a critical control point because the quality of the nut directly affects the flavor and texture of the final product. Optical sorters and vibrating sieves are used to remove debris, stones, and underdeveloped nuts. The selected hazelnuts are then subjected to a deshelling operation using mechanical crushers that crack the shells without damaging the kernels. These kernels are further inspected and cleaned before being sent to large-scale roasting units. Roasting is one of the most important flavor development stages in Nutella production. In industrial operations, continuous roasting ovens are used, where hazelnuts travel through a rotating drum or along a conveyor belt under a flow of hot air, typically between 140 to 160 degrees Celsius. Roasting duration and temperature are carefully controlled to bring out the nutty aroma and to reduce moisture to below 5%. After roasting, the nuts are cooled quickly to preserve their volatile aromatic compounds and prevent overcooking. The cooled hazelnuts are then transferred to grinding machines, where they are ground into a paste using roller mills and high-speed grinders. The result is a fine hazelnut paste with a smooth texture ready to be incorporated into the final mix. Meanwhile, other key ingredients are prepared in parallel. Sugar, which makes up a significant portion of the spread, is delivered in bulk as granulated white sugar. Before use, the sugar is pulverized in industrial fine grinders or pin mills until it becomes a powdered form with consistent particle size, often below 30 microns, to avoid any grittiness in the final texture. This powdered sugar is stored in silos and fed into the mixing tanks using pneumatic conveying systems. Cocoa solids, another essential ingredient, are typically received as cocoa powder. This powder undergoes sifting and magnetic separation to remove any foreign particles or metallic fragments. Skimmed milk powder and whey powder, both derived from dairy processing, are reconstituted into a slurry with water or added in dry form depending on the plant design. These milk-based ingredients contribute not only to flavor, but also to the creamy mouthfeel and protein content of the spread. Palm oil is selected for its semi-solid consistency at room temperature, which is ideal for producing a spreadable product that does not require refrigeration. Before blending, palm oil is filtered and heated to a controlled temperature to ensure uniform mixing. It is pumped into heated storage tanks, where it is kept in liquid form and circulated to prevent crystallization. Once all base ingredients are prepared, the process of mixing begins in large-scale stainless steel mixing tanks. These tanks are fitted with high-torque agitators and precision load cells that measure the exact quantity of each ingredient added. The powdered sugar, hazelnut paste, cocoa powder, milk powder, and palm oil are introduced sequentially, followed by small quantities of lecithin and vanillin. Lecithin acts as an emulsifier, allowing the fat-based palm oil to bind with the water-based milk components, ensuring the product remains stable and homogeneous. Vanillin, a synthetic or natural flavoring, gives Nutella its distinct sweet aroma. The mixture is subjected to a refining process to achieve the desired texture and particle size. This is often accomplished using 5-roll refiners or conching machines. The 5-roll refiner uses a series of precision-engineered steel rollers that progressively grind the mixture to a fine, uniform consistency, typically achieving particle sizes of around 20 microns. This stage is crucial for eliminating any detectable graininess, resulting in the smooth, velvety texture Nutella is known for. In some facilities, a conching step follows refining. In conching, the mixture is kneaded and aerated for several hours in large heated vessels. The process further develops flavor, reduces acidity, and allows volatile off flavors to evaporate. Temperature, shear force, and mixing speed are all tightly controlled to maintain product consistency. After conching, the mixture is cooled slowly to prevent separation and to stabilize the emulsion. Once the spread reaches the correct viscosity and temperature, it is pumped through sanitary pipelines to the filling stations. Filling lines are fully automated and consist of synchronized conveyor systems, rotary fillers, and capping machines. The jars, made from glass or plastic, are cleaned with compressed air or ionized air blowers before being filled. Filling heads dispense the exact amount of Nutella into each jar with remarkable precision, ensuring minimal variation between units. Immediately after filling, jars pass through a sealing station where a foil membrane is applied to the mouth of the jar. This step is critical for maintaining freshness and preventing microbial contamination. The foil seal is typically induction sealed using a non-contact electromagnetic process that heats the foil and causes it to bond to the jar rim. Once sealed, the jars are capped with tamper-evident lids and conveyed to labeling machines. High-speed labelers apply brand-specific labels with information such as batch number, expiration date, and ingredients. Each jar then proceeds through a series of quality control checkpoints. These include weight checks, vision systems to verify correct sealing and labeling, and metal detection to ensure product safety. Defective units are automatically rejected and diverted for reprocessing or disposal. The entire packaging area is designed with hygiene in mind, using positive air pressure zones, clean-in-place systems, and stainless steel surfaces to reduce contamination risk. After packaging, Nutella jars are grouped into cartons or shrink-wrapped multi-packs, then stacked on pallets using robotic arms. Pallets are stretch-wrapped and labeled with barcodes for inventory tracking. From here, the product enters the distribution phase. Nutella's distribution logistics are a finely tuned operation. Pallets are stored temporarily in climate-controlled warehouses where temperature and humidity are maintained to prevent oil separation or spoilage. Inventory management systems track product movement using real-time data. Distribution centers coordinate with retailers, wholesalers, and export logistics to move products efficiently. Nutella is shipped in refrigerated or insulated containers only when necessary, though its high fat, low moisture content gives it considerable shelf stability. Throughout its supply chain, Nutella maintains compliance with international food safety standards such as ISO 22000, BRC, and HACCP protocols. Auditors regularly inspect facilities for compliance, and the entire process from hazelnut sourcing to jar sealing is documented for traceability and recall readiness. Automation, data collection, and machine learning are increasingly used to optimize processes, predict maintenance needs, and reduce waste. What makes Nutella's production so compelling is the precise synchronization of global sourcing, advanced food engineering, and automation technologies that allow for the consistent output of millions of jars per day. Every batch is a result of not just culinary science, but also the collaboration of agronomists, engineers, food technologists, and supply chain experts. Beyond the factory floor, Nutella's evolution continues with reformulations aimed at reducing sugar or incorporating more sustainable palm oil. Efforts to use recyclable packaging and implement blockchain for ingredient tracking reflect broader industry trends towards transparency and environmental responsibility. The foundation of Jif begins with its primary ingredient, peanuts. Specifically, the variety used in commercial peanut butter production is often the runner peanut, prized for its uniform kernel size, mild flavor, and high oil content. These peanuts are primarily grown in the southeastern United States, including states like Georgia, Alabama, and Florida, where sandy soils and warm climates create optimal growing conditions. Jif, owned by the J.M. Smucker Company, works closely with peanut growers through long-standing contracts to ensure consistent quality and supply. Before the peanuts even reach the factory, they're subjected to extensive grading systems operated by the USDA, evaluating factors like kernel size, moisture content, and damage from mold or pests. Once harvested, the raw peanuts are cured by drying them to a safe moisture level, usually around 10%. This drying stage is essential to prevent mold growth during transport. The peanuts are then shelled using mechanical shellers that crack the outer holes while leaving the kernels intact. After shelling, the peanuts are cleaned using air classifiers and vibrating screens to remove debris, dirt, and remaining shell fragments. These cleaned kernels are then transported in bulk to Jif's dedicated peanut butter production facilities, where their transformation truly begins. Upon arrival at the factory, peanuts undergo a second round of cleaning and quality control. Optical sorters equipped with high-speed cameras and sensors scan each peanut at astonishing rates, removing any discolored, damaged, or foreign material contaminated nuts. Metal detectors are also employed at this stage to ensure there are no traces of metal debris from harvesting equipment. These steps are critical not only for food safety, but also for maintaining Jif's smooth and consistent flavor. The next stage is roasting, arguably the most important phase for flavor development. Industrial peanut roasters are highly sophisticated machines capable of handling thousands of pounds of peanuts per hour. Jif uses a continuous dry roasting process where peanuts are evenly fed onto a perforated conveyor belt that moves through a tunnel of hot, forced air. Temperatures during roasting typically range between 160 and 180 degrees Celsius, with exact values finely tuned based on peanut size, oil content, and desired flavor profile. This process typically takes 15 to 30 minutes and is closely monitored using infrared sensors and real-time moisture analyzers. As peanuts roast, their proteins and sugars undergo Maillard browning, creating hundreds of volatile aroma compounds that contribute to peanut butter's distinctive roasted flavor. Immediately after roasting, the peanuts are rapidly cooled using chilled air blowers to stop the cooking process and lock in the developed flavors. This cooling also prevents oil separation and oxidation, both of which can negatively impact product shelf life. At this point, the roasted peanuts are ready to be ground, but first they must be blanched. Blanching in peanut butter production refers not to cooking in water, but to the mechanical removal of the thin, papery red skins that surround the kernels. In Jif's facilities, peanuts are sent through dry blanchers, machines that tumble the nuts at high speeds while heated air loosens the skins. Rotating brushes then remove the skins entirely, and high-capacity vacuum systems suck away the debris. The blanched peanuts are now a light golden color and are inspected one final time before grinding. The grinding stage is where peanuts are turned into a thick, luscious paste. Jif's production lines use a two-stage grinding process to achieve the brand's famously smooth consistency. First, peanuts are coarse ground using heavy-duty industrial grinders. These machines use stainless steel burrs or hammer mills to crush the nuts into a semi-solid mass known as peanut paste. This paste still contains some coarse particles and has not yet achieved its final texture. Next, the coarse paste is fed into ultra-high-speed fine grinders, often colloid mills, which apply extreme shear forces to reduce particle size down to 10 to 15 microns. This is a crucial target, as particle size below 20 microns ensures a mouthfeel that is perceived as completely smooth by consumers. During this stage, other ingredients are also introduced into the mixture. These include sugar, fully hydrogenated vegetable oils, salt, and sometimes molasses or mono and diglycerides. The oils, often made from rapeseed, cottonseed, or soybean, are used to stabilize the peanut butter and prevent oil separation on the shelf. Unlike palm oil or liquid vegetable oil, fully hydrogenated oils remain solid at room temperature and help give Jif its stable texture without requiring stirring. These additional ingredients are metered in with extraordinary precision using automated dosing systems connected to load cells and flow meters. Inline mixers ensure that each component is fully dispersed throughout the peanut paste. The temperature during grinding is carefully controlled, typically held between 60 and 75 degrees Celsius, to keep the product fluid without degrading flavor compounds. Once the peanut butter has been ground to the desired texture and all ingredients are thoroughly incorporated, it enters a holding tank under nitrogen blanketing. This protective gas layer prevents oxidation and helps preserve freshness during the short holding period before packaging. The product is then pumped to the filling lines through a network of heated sanitary stainless steel piping. Jif's packaging lines are models of efficiency and automation. Plastic jars, blow molded from PET or HDPE, are automatically unscrambled and conveyed into position. Before filling, jars pass through an air rinse station that uses ionized air to remove dust or plastic fragments. High-speed rotary piston fillers dispense precise volumes of peanut butter into each jar, minimizing air entrapment to avoid spoilage and maintain shelf life. Filled jars are then capped immediately using torque-controlled capping heads that screw on tamper-evident lids. After capping, jars pass through induction sealers where a foil membrane is bonded to the jar rim. This step uses electromagnetic energy to heat and seal the foil in milliseconds, creating a hermetic barrier that locks in flavor and protects against microbial contamination. The sealed jars move to labeling machines, where front and back labels are applied, followed by laser or inkjet printers that mark each jar with batch codes, production dates, and plant IDs. Throughout this packaging process, quality control is constant and rigorous. Automated vision systems inspect each jar for correct fill height, proper labeling, and cap placement. Metal detectors and X-ray scanners identify any contamination before product leaves the factory. Random samples are also pulled for texture analysis, oil separation testing, sensory panels, and microbiological screening. Any deviation from specifications leads to immediate corrective actions, and defective jars are removed from the line. Packaged jars are grouped into corrugated cardboard cases using robotic case packers. These cases are palletized by programmable robotic arms and stretch wrapped to ensure stability during transport. Each pallet receives a barcode label integrated into Jif's warehouse management system, allowing for real-time traceability from production to point of sale. Once palletized, the finished peanut butter is moved to distribution centers equipped with temperature and humidity control. Although Jif peanut butter is shelf-stable and does not require refrigeration, maintaining moderate temperatures during warehousing and shipping helps preserve flavor and prevent oil migration or texture degradation. From these central hubs, Jif is shipped to retailers, wholesalers, and export customers across the country and around the globe. The journey from raw peanut to finished jar is guided not only by mechanical precision, but also by a deep understanding of food chemistry, microbiology, logistics, and consumer expectations. Behind the familiar red-lidded jar is a network of engineers, food scientists, supply chain analysts, and production operators, all working in synchrony to ensure that every spoonful of Jif meets exacting standards. Advancements in automation and data analytics continue to refine the process. Modern Jif facilities are equipped with real-time monitoring systems, predictive maintenance software, and even machine learning algorithms that optimize roasting profiles based on moisture content and kernel density. Environmental controls ensure energy efficiency and waste reduction, and partnerships with peanut growers include sustainability initiatives aimed at soil conservation and water use reduction. The story of Hershey's syrup begins with its core ingredients: cocoa, sugar, water, corn syrup, salt, preservatives, and a few functional additives like potassium sorbate and xanthan gum. Each of these components is sourced with meticulous care to ensure consistency and food safety. Cocoa powder, the primary flavoring agent, is typically sourced from West Africa, where the Hershey Company partners with certified cooperatives to encourage sustainable farming practices. The cocoa beans are fermented, dried, and shipped to the US, where they are roasted, ground, and pressed into cocoa cake. This cake is then pulverized into a fine cocoa powder, standardized for fat content, flavor profile, and color intensity. Upon arrival at Hershey's syrup production facilities, all ingredients undergo rigorous testing. The cocoa powder is checked for microbiological safety, color consistency, particle size, and moisture levels. Sugar, often in granulated form, is tested for crystal uniformity, purity, and absence of foreign materials. Corn syrup, used as both a sweetener and thickener, is delivered in tanker trucks and stored in heated silos. It is continuously circulated to prevent crystallization or microbial growth. Water used in the process is treated on-site, filtered, softened, and sanitized using UV light or reverse osmosis to ensure purity and microbial control. The first major production stage is blending the dry and liquid ingredients. The process typically starts with the creation of a sugar corn syrup slurry. In large stainless steel jacketed mixing tanks, granulated sugar is combined with warm water and corn syrup under controlled agitation. These tanks are equipped with variable speed mixers and internal temperature sensors to maintain optimal dissolution rates. The heating jackets help bring the mixture to a consistent temperature, usually between 55 and 70 degrees Celsius, to accelerate solubility while avoiding caramelization. Once a uniform syrup base is achieved, cocoa powder is added. However, dry cocoa is notoriously difficult to hydrate due to its high fat content and fine particle size, which cause it to float and form lumps when introduced to liquid. To overcome this, Hershey's production lines utilize high shear mixers and vacuum-powered powder feeders. The vacuum system pulls cocoa powder directly into the liquid stream, minimizing clumping and ensuring uniform dispersion. Simultaneously, high-speed rotor-stator mixers or inline homogenizers shear the mixture at thousands of RPMs, breaking down any agglomerates and producing a velvety, uniform chocolate syrup base. At this stage, salt and preservatives such as potassium sorbate are also introduced. These additions are precisely dosed using automated ingredient hoppers that weigh each component before releasing it into the blanders. Potassium sorbate acts as a mold and yeast inhibitor, extending the product's shelf life. Some formulations may also include citric acid or sodium citrate to adjust pH, which affects both microbial stability and flavor brightness. The syrup then enters the cooking phase. Unlike batch cooking in traditional kitchens, industrial syrup production uses continuous flow heating systems. The chocolate slurry is pumped through tubular or plate heat exchangers, where it is heated rapidly to pasteurization temperatures, typically between 85 and 95 degrees Celsius. This thermal treatment destroys any remaining microbial contaminants and activates the emulsifiers and stabilizers added in earlier steps. The product is held at this temperature for a specific dwell time as it flows through holding tubes, ensuring regulatory compliance with pasteurization standards. After cooking, the syrup must be cooled quickly to prevent overcooking and maintain the desired viscosity and flavor. This is achieved using chilled water heat exchangers, which rapidly bring the syrup down to below 30 degrees Celsius. Rapid cooling also helps stabilize the emulsion, locking in the texture and preventing ingredient separation. The cooled syrup is then transferred to intermediate holding tanks, where it is gently agitated and blanketed with nitrogen gas to minimize oxidation. At this point, the syrup undergoes several quality control checks. Samples are pulled and tested for viscosity using rotational viscometers, ensuring that the pourability matches the brand's standard profile. Colorimeters assess chocolate intensity and hue, while refractometers measure sugar concentration. In parallel, sensory panels may be employed to evaluate flavor, mouthfeel, and aroma. Microbial testing is conducted on every batch to confirm that pasteurization was effective and that no contamination has occurred. Once the product passes quality control, it is sent through final filtration before packaging. Fine mesh inline filters remove any particulate matter that may have formed during cooking or cooling. This ensures a perfectly smooth syrup with no grit or undissolved solids. Packaging Hershey's syrup involves a highly synchronized series of steps designed for both hygiene and speed. The most common containers are squeezable plastic bottles, which are blow molded from PET or HDPE on site or delivered pre-formed. These bottles are first conveyed through an air rinse system that blasts ionized air to remove dust or debris. They are then indexed into position beneath the filling nozzles. Filling is performed using servo-controlled, volumetric, or piston fillers. These machines are calibrated to deliver exact quantities of syrup, typically in the range of 650 to 800 grams per bottle, depending on size. The syrup is dispensed at controlled speeds to prevent splashing or air entrapment. No drip filling heads are often used to maintain clean bottle exteriors and reduce product waste. After filling, the bottles move to the capping station. Caps are sorted using centrifugal feeders and applied using torque-monitored capping heads, which ensure a tight seal without over-tightening. Each bottle is then passed under an induction sealer, where an aluminum foil seal is bonded to the bottle mouth using electromagnetic heating. This tamper-evident seal not only enhances shelf life, but also guarantees product integrity. Next, the bottles pass through a labeling machine where pressure-sensitive labels are applied with exacting precision. Labels include not just branding and nutrition information, but also critical traceability codes, including batch numbers, timestamps, and plant identifiers. These details are laser-etched or printed using inkjet coders. Before leaving the line, every bottle passes a series of automated inspection stations. Vision systems equipped with high-speed cameras check for correct fill levels, cap placement, seal integrity, and label alignment. Any non-conforming product is rejected and diverted to a separate inspection area for manual review. Approved bottles are grouped into cartons or shrink-wrapped multi-packs. Robotic case packers load the bottles into boxes, which are then sealed, labeled, and palletized. These pallets are stretch-wrapped and tagged with scannable barcodes for warehouse tracking. The entire process from filling to palletization is fully integrated into Hershey's manufacturing execution system, allowing for real-time monitoring and inventory control. Palletized syrup is transported to climate-controlled distribution centers. While Hershey's syrup is shelf-stable, temperature extremes can still impact viscosity and appearance. Warehouses maintain stable conditions to prevent thickening in cold weather or oil separation in high heat. From there, the product is dispatched to retail partners, online fulfillment centers, and export destinations. Throughout the supply chain, Hershey's implements strict food safety protocols, including compliance with the Global Food Safety Initiative, hazard analysis and critical control points, and FDA regulations. Traceability is maintained from raw cocoa bean to finished bottle, ensuring any issue can be traced and contained within hours. What makes Hershey's syrup so enduring in the marketplace isn't just its flavor, it's the precision and consistency made possible through modern food engineering. Every step of the process, from the aggressive mixing of cocoa powder to the final induction seal, is executed with scientific rigor. Equipment calibration, ingredient testing, and continuous improvement protocols ensure that each bottle tastes the same, pours the same, and satisfies the same cravings generation after generation. As the brand moves forward, sustainability is becoming an even greater focus. Efforts to reduce plastic use in packaging, improve energy efficiency in heating and cooling systems, and source more ethical cocoa are all part of Hershey's long-term production goals. Some lines are exploring bio-based PET alternatives for bottles and increasing recycling within plant operations. Continuous feedback from quality assurance teams and customer satisfaction metrics are used to refine processing parameters and optimize flavor retention across product shelf life. In the massive production facilities where Reese's peanut butter cups are made, the process begins well before any chocolate is poured or any peanut butter is mixed. It starts with sourcing two critical ingredients: high-quality peanuts and specially formulated chocolate. The peanuts arrive at the plant in large, tightly sealed containers, having already undergone preliminary sorting at dedicated processing centers. However, the Reese's factory does not take any chances. Upon arrival, each shipment of peanuts is sampled and tested for aflatoxins, moisture content, and flavor quality. Only the best peanuts pass through to the next stage. The first critical transformation begins in the peanut roasting room, a cavernous area lined with continuous batch roasters. These machines look like giant horizontal drums that rotate slowly, while hot air circulates inside, ensuring each peanut is evenly toasted to bring out its natural oils and enhance flavor. Temperatures inside the roasters are tightly controlled, typically between 300 and 350 degrees Fahrenheit, and the roasting cycle can last anywhere from 10 to 30 minutes, depending on peanut size and desired roast level. Workers monitor color readings using optical sensors, making slight adjustments to the roast if necessary to achieve that signature Reese's flavor. Once roasted, the peanuts are transferred via conveyor belts to powerful cooling tunnels. Giant fans blow chilled, filtered air over the peanuts to halt the roasting process immediately, locking in the flavor profile. After cooling, the peanuts pass through a series of magnetic separators and vibrating screens to remove any foreign materials or remaining shell fragments, ensuring absolute purity. Next comes the grinding phase. The roasted peanuts are funneled into industrial grinders, massive machines equipped with heavy-duty steel plates that spin at high speeds. The first grind reduces the peanuts into a rough paste. Then a secondary, finer grind transforms the mixture into the silky, smooth peanut butter that will fill every cup. During grinding, small amounts of sugar, salt, and a plant-based emulsifier are added to stabilize the peanut butter and give it the slightly sweet, distinctly savory flavor that fans recognize instantly. The temperature is carefully managed during this phase, usually kept between 120 and 140 degrees Fahrenheit to ensure the oils remain stable and the texture remains creamy but not runny. The freshly made peanut butter is then pumped into enormous stainless steel holding tanks, where it is kept warm and agitated gently to maintain a consistent texture. These tanks are connected by sanitary piping to the production lines, allowing for seamless and hygienic movement of the peanut butter when it's time to fill the cups. Meanwhile, the chocolate preparation is already underway in a different section of the factory. Reese's uses a specially formulated milk chocolate blend that balances sweetness, cocoa flavor, and a creamy melt-in-the-mouth texture. Bulk chocolate arrives in the form of large solid blocks or liquid tanker shipments, depending on the factory's setup. If solid, the chocolate is first broken down in massive pre-melters, slowly heating it to around 110 degrees Fahrenheit to achieve a uniform, molten state. Once liquefied, the chocolate is pumped into tempering machines, sophisticated systems that cool and reheat the chocolate in a precise curve to stabilize the cocoa butter crystals. This tempering process is critical. It gives the finished cups their glossy appearance, firm snap, and excellent shelf stability. Now, with both chocolate and peanut butter ready, the cup assembly line begins. First, paper cup molds are automatically dispensed onto a continuously moving conveyor belt. High-speed chocolate depositor machines then squirt a carefully measured amount of molten chocolate into each paper cup, forming the base layer. The conveyor belt vibrates gently to help the chocolate settle evenly across the bottom and slightly up the sides of each mold. Immediately after this, the conveyor moves the cups through a cooling tunnel, where chilled air at around 50 degrees Fahrenheit partially solidifies the base chocolate layer. This quick cooling ensures that when the peanut butter is deposited, it won't sink all the way to the bottom of the cup, maintaining the ideal layered structure. Next, the creamy peanut butter is deposited into the center of each chocolate base using precision nozzles. The amount of peanut butter is meticulously controlled by programmable pumps, ensuring every Reese's cup has the same perfect peanut to chocolate ratio. Interestingly, the peanut butter filling itself is slightly cooler than the chocolate, typically around 80 to 90 degrees Fahrenheit, which helps it stay firm during the next stages of production. After the peanut butter is deposited, a second layer of molten chocolate is dispensed over the top, sealing in the peanut butter and forming the upper shell of the candy. Again, careful vibration of the conveyor ensures a smooth, even surface. At this point, visual inspection systems using high-speed cameras and AI algorithms scan the cups for consistency, checking fill levels, alignment, and any surface imperfections. Defective cups are automatically rejected from the line. The filled cups then pass through an extended cooling tunnel where they spend several minutes gradually chilling back down to around 45 degrees Fahrenheit. This staged cooling prevents the chocolate from blooming, a condition where cocoa butter rises to the surface and creates an unsightly white film. Instead, the cooling process locks in that deep, shiny chocolate sheen. Once fully cooled, the cups are ready for packaging. Automated robotic arms gently lift rows of finished Reese's cups and place them into pre-formed trays or directly onto flow wrapping machines. Each candy is enveloped in a thin, protective layer of branded orange packaging film. Heat sealers quickly fuse the edges of the wrapper shut, trapping a pocket of nitrogen gas inside. This inert atmosphere helps prevent oxidation, preserving freshness and flavor for extended shelf life. The wrapped candies are then grouped into multi-packs by high-speed cartoning machines, which fold and seal cardboard boxes around designated numbers of cups, whether it's a standard 2-pack, a king-size 4-pack, or a family-size bag of miniatures. These boxes are coded with manufacturing dates, lot numbers, and other traceability data before being stacked neatly onto pallets. Before the pallets leave the factory, a final quality control check is performed. Random packages are pulled from the line and subjected to a battery of tests, including weight checks, taste tests, visual inspections, and even X-ray analysis to ensure there are no contaminants or structural flaws inside the candies. Only when these samples pass inspection are the pallets shrink-wrapped and labeled for distribution. From there, the Reese's Cups embark on their journey through a highly coordinated supply chain. Pallets are loaded onto refrigerated trucks, kept at cool but not freezing temperatures to prevent the chocolate from melting or degrading. Distribution centers across the country receive the shipments, from which they are sent to grocery stores, convenience shops, vending machine suppliers, and even directly to online retailers. What's fascinating about the Reese's production process is how every detail, temperature, timing, movement is optimized for both speed and quality. The factories are largely automated, with programmable logic controllers and centralized computer systems coordinating every phase, minimizing human error and maximizing consistency. Maintenance crews monitor the machinery continuously, ready to intervene if even the slightest deviation occurs. Yet, despite the heavy automation, a skilled team of chocolatiers, food scientists, and process engineers oversee operations daily, ensuring that the soul of the Reese's Cup, the perfect balance of creamy peanut butter and silky milk chocolate, is never compromised. In recent years, new technologies have further enhanced production. Advanced predictive maintenance uses AI algorithms to detect early signs of equipment wear, preventing costly downtime. Robotic packaging systems have become faster and more flexible, adapting to different product formats with minimal reprogramming. Even energy efficiency has improved dramatically, with modern factories recapturing waste heat from the roasting and tempering processes to reduce overall power consumption. The result of all this effort is what you hold in your hand, a Reese's Peanut Butter Cup with the same incredible taste that has delighted generations. From careful peanut selection to intricate chocolate tempering, from the first squirt of chocolate to the final seal of the wrapper, every step is a marvel of precision, engineering, and culinary artistry, ensuring that each bite delivers the unmistakable Reese's experience, time after time. The making of Hershey's milk chocolate begins long before any bars are molded or wrapped. It starts with sourcing one of the world's most essential commodities, cacao beans. Hershey's purchases massive quantities of cacao from regions like West Africa, Central and South America, and parts of Southeast Asia. Upon arrival at Hershey's specialized facilities, the cacao beans undergo strict quality control protocols. Sampling machines pull randomized beans from each shipment, checking for mold, contamination, fermentation quality, and flavor profiles. Only beans that meet Hershey's high standards proceed to production. The first major operation is cleaning. Beans travel through a series of shaking screens, magnetic separators, and powerful air jets that remove debris like sticks, stones, and dust. Once cleaned, the beans are routed to the roasting department. Here, colossal stainless steel drum roasters, each capable of handling thousands of pounds per batch, bring the beans up to roasting temperatures of around 250 to 300 degrees Fahrenheit. This roasting phase is crucial. It not only develops the rich cocoa flavors, but also loosens the shell from the nib, the part of the bean that will become chocolate. After roasting, the beans pass through cracking and winnowing machines. Heavy rollers crack the beans open, and powerful airflows then separate the lighter, papery shells from the heavier cocoa nibs. The nibs are collected and sent immediately into the refining phase. The shells, interestingly, don't go to waste. Many are repurposed as agricultural mulch or used in animal feed. The next transformation happens in the grinding rooms. Industrial grinders crush the nibs into a thick, gritty paste known as chocolate liquor. Despite its name, it contains no alcohol. Giant stone mills or modern ball mills spin tirelessly, reducing particle sizes to less than 100 microns. This grinding process releases the cocoa butter within the nibs, turning the dry nibs into a fluid, rich mass. At this stage, the chocolate liquor is either stored or immediately processed depending on the specific recipe being produced. For Hershey's signature milk chocolate, chocolate liquor alone is not enough. It must be blended with several other ingredients: sugar, milk, and cocoa butter, among others. Hershey's famously uses fresh condensed milk rather than powdered milk, a technique that imparts its distinctive flavor. Tankers bring in condensed milk that has already been pasteurized and quality tested for microbial safety. The milk is combined with sugar in large stainless steel kettles and cooked to form what is known as a milk crumb, a dry, sweet, caramelized powder that becomes the base for Hershey's milk chocolate. The milk crumb, chocolate liquor, and additional cocoa butter are blended together in massive mixers that resemble horizontal cement mixers but are built for food-grade standards. In these tumbling vessels, the blend of ingredients becomes a coarse chocolate dough. This dough is then fed through refining rollers, 5 or 6 massive polished steel rollers stacked horizontally. As the dough passes through each successive roller gap, it is compressed and sheared finer and finer, reducing the sugar and cocoa particles to just the right microscopic size to ensure a smooth texture. At this point, the chocolate still lacks the silky consistency and full flavor that people expect. That's where one of the most crucial steps in chocolate making enters: conching. Hershey's uses giant conching machines, massive, heavy-duty mixers with granite rollers that agitate, aerate, and warm the chocolate dough for hours. Traditional conching could take up to 72 hours, but with modern methods and specialized Hershey's technology, the time has been optimized without sacrificing quality. During conching, volatile acids and bitter flavors evaporate away, while cocoa and milk flavors mellow and deepen. At the same time, the continuous mixing further reduces any remaining coarse particles and disperses the cocoa butter thoroughly throughout the mass. Temperature control during conching is critical. The chocolate must stay within an exact range, typically between 130 to 180 degrees Fahrenheit, depending on the desired flavor development. Ventilation hoods draw off unwanted volatiles, and sensors embedded throughout the conches constantly report data back to automated control systems, adjusting speed and temperature as needed. Following conching, the chocolate moves into the tempering phase. Tempering is an art and science all its own. Chocolate is carefully cooled and reheated through specific temperature curves to create stable cocoa butter crystals. This gives finished chocolate its snap, gloss, and resistance to melting at room temperature. Hershey's uses continuous tempering machines, which can process thousands of pounds per hour. These machines use a series of heated and cooled zones to guide the chocolate through its crystal formation journey with pinpoint accuracy. Improper tempering would result in chocolate that's dull, crumbly, or prone to blooming, a white discoloration, so this step must be executed flawlessly. Once tempered, the liquid chocolate is transported through heated pipes to the molding stations. There, automated depositors squirt precise amounts of chocolate into endless arrays of molds, some shaped for classic Hershey's bars, others for miniature versions or seasonal specialties. The molds vibrate rapidly on oscillating tables to eliminate any air bubbles and ensure an even surface. The molds then enter a long cooling tunnel, a carefully calibrated environment where the chocolate solidifies slowly and evenly. Inside the tunnel, the temperature drops gradually from around 70 degrees Fahrenheit to about 50 degrees, preventing thermal shock and ensuring that the chocolate sets with a fine, smooth crystal structure. After cooling, the solid chocolate is demolded. High-speed mechanical arms flip and flex the molds, gently releasing the perfectly formed bars onto conveyor belts. At this stage, visual inspection systems equipped with high-speed cameras and AI check every piece for uniformity, detecting even minor surface defects or molding errors. Imperfect chocolates are removed from the line for recycling back into the production process. The next step is packaging. For Hershey's bars, the chocolate rides conveyors into flow wrapping machines. Each bar is enveloped in a tight sleeve of foil and then an outer branded paper wrapper. Modern flow wrappers work at astonishing speeds, often wrapping hundreds of bars per minute with perfect precision. The wrapped bars are coded with expiration dates, batch numbers, and tracking information to ensure full traceability from production through to sale. Once wrapped, the bars are collated into cartons or retail trays by robotic packers, which arrange them neatly in boxes that are then sealed, labeled, and stacked onto pallets. Before shipment, a random sample from every production batch undergoes additional quality assurance tests, including break tests, melt tests, taste panels, and microbial analysis. Only after passing all these checks are the pallets released for distribution. The finished Hershey's milk chocolate bars then enter the logistics phase, moving through regional distribution centers that coordinate delivery to supermarkets, convenience stores, cinemas, and countless other retailers around the world. Throughout the distribution chain, temperature control remains critical. Warehouses and trucks are climate controlled to prevent the bars from experiencing temperature swings that could cause chocolate bloom or textural changes. Throughout the entire factory process, Hershey's leverages advanced automation, continuous monitoring, and decades of chocolate-making expertise to ensure that every bar tastes as iconic and consistent as the last. The level of control is extraordinary. Chocolate viscosity, particle size distribution, moisture levels, and flavor profiles are measured and adjusted in real time using sophisticated inline sensors and laboratory tests. In recent years, Hershey's has also invested heavily in sustainability, working directly with cocoa farmers through its Cocoa for Good program to promote ethical sourcing, better farming practices, and environmental stewardship. This commitment ensures not just the continued availability of high-quality cacao, but also a better future for the communities that produce it. The journey of a Kit Kat begins with two major components: the chocolate coating and the crisp wafer core. Both are manufactured separately and in parallel streams before being married together into the unmistakable Kit Kat form. Each ingredient, each layer, and each step is engineered with astonishing precision to create the perfect snap, crunch, and creamy finish that Kit Kat is famous for. The process starts with the preparation of the chocolate. Kit Kat's signature coating is slightly different from pure chocolate. It is technically a compound chocolate, specially formulated to give a smooth melt and quick setting properties ideal for enrobing wafers. At factories like Nestlé's York facility in the UK or similar plants worldwide, bulk cocoa liquor, cocoa butter, sugar, and milk solids are combined. The cocoa beans that form the basis of the liquor are sourced from sustainable suppliers, cleaned, roasted, and ground into fine paste months before production even begins. To prepare the chocolate coating, the cocoa liquor is blended with sugar and powdered milk in enormous stainless steel mixers. This mixture is then refined through a series of precision-calibrated rollers, reducing the particle size to around 20 microns, finer than the human tongue can detect. The refining phase is essential to create the smooth mouthfeel Kit Kat lovers expect. Following refinement, the chocolate mass moves into conching machines, where it is slowly mixed, aerated, and heated. This removes any bitter flavors and unwanted acidity, while promoting the development of a creamy, caramel-like flavor that defines Kit Kat's chocolate. Temperature control during conching is rigorously maintained at around 135 to 180 degrees Fahrenheit, depending on the recipe. Once the chocolate reaches the right flavor and viscosity, it is moved into tempering units, where it's carefully cooled and reheated to produce stable cocoa butter crystals. Proper tempering ensures that the finished chocolate will have a shiny appearance, a satisfying snap, and resistance to blooming. Meanwhile, in another section of the factory, the production of the wafer sheets is underway. Wafer batter, made from a simple mixture of wheat flour, sugar, vegetable oil, leavening agents, and water, is mixed in giant, computer-controlled vats. The batter is pumped through piping systems directly to high-speed wafer baking ovens, each stretching tens of meters in length. These wafer ovens consist of two continuously moving steel belts that sandwich the batter and pass through a baking tunnel. As the belts travel, radiant heat, conduction, and convection work together to bake the batter into ultra-thin, crisp wafer sheets. Each sheet emerges from the oven perfectly cooked, around 2 to 3 millimeters thick, with a delicate, light texture and a uniform golden brown color. After baking, the wafer sheets are rapidly cooled using forced chilled air to prevent moisture absorption. They are stacked and transported via conveyor belts to the cream spreading stations. Here, a thin layer of specially formulated filling, a mixture typically based on ground wafer crumbs, vegetable fats, sugar, and milk solids, is evenly spread across the wafers. The filling not only enhances the flavor, but also acts as a structural adhesive, bonding the multiple wafer layers together. Usually, 3 or 4 wafer sheets are stacked, with cream filling between each layer. These multi-layered blocks are then pressed under controlled pressure to ensure perfect bonding without cracking or crushing the delicate wafers. After resting for stabilization, the wafer blocks are transferred to high-speed cutting machines. The cutting process is a masterpiece of mechanical precision. Using laser guides and ultrasonic blades, the blocks are sliced first longitudinally, then crosswise into the familiar slim Kit Kat finger dimensions. Every cut must be perfect. Any deformation could later disrupt the enrobing process or spoil the iconic snap experience. Once cut, the wafer fingers are ready for enrobing. Conveyors carry them through a chocolate waterfall inside the enrobing machines. A curtain of tempered Kit Kat chocolate cascades over the wafers, completely coating them on all sides. Excess chocolate is blown off the bottom with controlled air jets, creating the thin chocolate layer underneath that gives Kit Kat its balanced chocolate to wafer ratio. Directly after enrobing, the fingers pass through a vibrating section of the conveyor to settle the chocolate coating and eliminate air bubbles. They then enter a series of cooling tunnels where cold, dry air, typically kept between 40 and 50 degrees Fahrenheit, slowly solidifies the chocolate coating without causing condensation, which would ruin the texture. At this point, the individual fingers are grouped together. Kit Kat is traditionally made with 4 fingers to a bar, although mini versions, single fingers, and chunkier variants are also produced. Robotic arms align and group the fingers with exact spacing between them before feeding them into wrapping machines. Kit Kat's iconic red and white wrapper is a masterpiece of branding and practical design. Wrapping is done using ultra-fast flow wrappers that synchronize perfectly with the grouping conveyors. Each set of fingers is enveloped in foil or a plastic laminate film, which protects against moisture and oxygen while maintaining the crunch of the wafer and the smoothness of the chocolate. The wrapping machines heat seal the edges at high speed, and rollers gently press and fold the sealed packs for that crisp, tight package finish Kit Kat is known for. As the wrapped bars move down the line, high-speed scanners and cameras inspect each package for correct seal integrity, label placement, and print clarity. Imperfections are detected in milliseconds, and defective packs are automatically ejected into collection bins for recycling. Once the Kit Kats are individually wrapped, the next stage is boxing and palletizing. Robotic case packers arrange the wrapped bars into boxes or display cartons, which are then sealed with automatic tapers and labeled with tracking information. Each box is carefully weighed and scanned to ensure it matches target specifications before being stacked onto pallets by robotic arms or palletizing machines. Throughout the entire production process, rigorous quality control is applied at every major step. Samples of chocolate, wafer batter, finished wafers, and completed bars are pulled at regular intervals for lab analysis. These tests include moisture content checks, microbiological safety testing, taste panels, and break strength tests to ensure the classic crisp break of a Kit Kat remains perfect batch after batch. In addition to inline testing, larger batch samples are subjected to accelerated aging studies to simulate how the product will perform over its shelf life. sensory evaluation booths, staffed by trained taste testers, ensure that every batch maintains the exact flavor, aroma, texture, and mouthfeel that consumers expect. Once the Kit Kats are boxed and palletized, they are shipped out from climate-controlled distribution centers. Transport conditions are carefully managed to prevent temperature fluctuations that could cause chocolate bloom or wafer softening. Many shipments are refrigerated during summer months or in hotter climates to guarantee the product arrives in prime condition. Kit Kat's industrial production is a brilliant choreography of automation, sensory science, and quality management. Despite the high level of automation, human oversight remains crucial. Line operators monitor critical control points, adjust machine settings, respond to alarms, and carry out maintenance to keep the lines running smoothly, often 24 hours a day, 7 days a week. Recent advancements have further refined the process. State-of-the-art production lines now incorporate AI-driven predictive maintenance, allowing engineers to anticipate mechanical failures before they happen. Machine learning algorithms also optimize ingredient mixing, cooking times, and cooling profiles, subtly adjusting for real-time variables like humidity, ingredient lot variation, or slight temperature shifts in the facility. Kit Kat's commitment to sustainability is woven into production as well. Modern factories are equipped with energy recovery systems that reuse heat from the ovens and chillers. Water used in cooling and cleaning processes is recycled wherever possible. Additionally, Kit Kat's cocoa is 100% sourced through programs like Rainforest Alliance certified farms, ensuring ethical and environmentally responsible cocoa farming practices. Each Kit Kat bar that makes it into a consumer's hands is the end product of thousands of micro decisions and perfectly tuned processes: baking, layering, cutting, coating, cooling, wrapping, all executed with a level of precision that would make a Swiss watchmaker proud. The crisp snap of the break, the lightness of the wafer, the creamy melt of the chocolate. Every detail is the result of decades of research, refinement, and relentless pursuit of chocolate and wafer perfection. The production of a Mars bar begins with the formulation and creation of its first major internal layer, the nougat. This nougat isn't the brittle kind you might find in traditional nut candies. Rather, it's a whipped, creamy, slightly chewy foundation that gives Mars bars their signature texture. Creating this nougat at industrial scale is a carefully engineered process that blends confectionery science with mass production machinery and strict environmental controls. Before the first batch of nougat is made, however, the ingredients themselves must be prepared and stored according to strict protocols. The base ingredients for the nougat are sugar, glucose syrup, water, fat typically palm or shea oil, dried milk powder, cocoa powder, and whipped egg white or egg albumin. All these materials arrive at the Mars manufacturing facility in bulk, delivered in tankers, tote bags, or sealed sacks. Each delivery is logged, barcoded, and entered into the site's inventory system. But before any ingredient enters production, it must pass Mars internal quality standards. All dry ingredients, such as sugar and milk powder, are transferred into enclosed silo systems using pneumatic conveyors. These silos are climate controlled and fitted with HEPA filtration to prevent contamination from dust or ambient air. Each ingredient batch is tagged with a barcode that traces it back to its supplier, production date, and previous storage conditions. For example, sugar may be tested for grain size, purity, and color using laser granulometry and ICUMSA color unit analysis. If it's outside tolerance, it's rejected immediately. Liquid ingredients like glucose syrup and oils are offloaded into jacketed stainless steel storage tanks through filtered, food-grade hoses. These tanks maintain the ingredients at set temperatures to ensure proper viscosity for pumping during production. Glucose syrup, for instance, is kept at around 40 degrees Celsius to remain fluid enough to move through piping without crystallizing. Oils are similarly heated and agitated to prevent separation or solidification. Once all components have been approved and staged, the first step in actual nougat production begins in a dedicated mixing chamber. This space is sealed off from other parts of the factory and maintained at specific humidity and temperature levels to preserve the quality and structure of the aerated product. Airborne particles are filtered through a multi-stage air filtration system, and stainless steel surfaces are sanitized before each production run. Nougat is made in large capacity continuous mixers, automated machines that blend ingredients while precisely managing flow rate, temperature, and mixing speed. In a traditional batch process, workers would mix sugar and glucose syrup with water and cook it to a specific temperature. But in Mars's high-speed factories, this process is carried out on a continuous flow basis, meaning raw ingredients are metered into the cooking system in real time, mixed, cooked, and then aerated in a constant stream. First, sugar, glucose syrup, and water are combined in a jacketed mixing vessel and brought up to temperature using indirect steam heating. The mixture must reach roughly 115 to 120 degrees Celsius, hot enough to dissolve all solids and achieve the correct consistency for whipping, but not so hot that caramelization occurs. Inline refractometers monitor the Brix level, sugar concentration, constantly, sending digital signals to a control system that adjusts syrup feed rate or cooking temperature as needed to stay within spec. Once the syrup reaches target temperature and concentration, it's transferred to a cooling chamber, where it's rapidly brought down to around 70 to 80 degrees Celsius using chilled water jackets. This temperature reduction is critical. It stabilizes the syrup mixture and prepares it for aeration with egg whites or albumin, which cannot be added while the base is too hot without denaturing the proteins. Now comes the aeration stage, where the characteristic lightness and chew of the nougat is created. A pre-prepared egg albumin solution is metered into the cooled sugar syrup in a continuous aerator. This machine functions much like a planetary mixer, but at vastly greater speed and scale. Blades spin at extremely high RPMs inside a sealed chamber, while air is injected under pressure. The result is a fluffy, stable foam that has the volume and consistency of whipped marshmallow. The air injected into the aerator is sterile and dry, supplied by an inline compressed air system equipped with microbial filters and dehumidifiers. Pressure, temperature, and air-to-liquid ratio are all controlled automatically via programmable logic controllers, PLCs, which adjust mixing speed and flow rate to maintain uniform aeration. If the density of the nougat mixture falls outside of target specifications, measured by inline densitometers, the system automatically corrects the air or syrup flow or alerts operators to intervene. At this point, cocoa powder and dried milk are added to the base. These ingredients give Mars Bar Nougat its unique color and rich malted taste. They are added using powder feeders that continuously meter the dry materials into the aerated mass as it exits the mixer. This blending occurs in a sealed paddle mixer with gentle, controlled agitation to avoid collapsing the foam structure. The resulting mixture is a warm, chocolatey nougat paste with a light, stable structure and a semi-elastic texture. Now that the nougat base is formed, it must be shaped and cooled. The nougat flows out of the mixer onto a stainless steel conveyor belt, forming a continuous slab about 2 to 3 centimeters thick. This slab passes through a chilling tunnel, where it is gradually cooled from around 60 degrees Celsius to just below ambient temperature. The tunnel uses recirculated cold air, zoned in multiple sections, to cool the nougat evenly without inducing condensation or hardening the outer surface too quickly. As the slab exits the chilling tunnel, it enters a cutting station. Rotary guillotine knives, synchronized with the belt speed, slice the slab crosswise into narrow ribbons, each of which will become the base layer of a Mars bar. These ribbons are then cut lengthwise by inline blades or ultrasonic cutters, creating rectangular nougat centers of uniform size. Every bar section is scanned by vision systems to check for dimensional consistency, length, width, and height, with auto-reject mechanisms removing any pieces that fall outside tolerance. The formed nougat segments are now ready to receive their second major component, the caramel layer. But before caramel is deposited, the nougat sections are spaced and aligned using lane diverters and product guides, ensuring that each bar proceeds uniformly through the next phase of production. The segments then pass into a buffer zone where their temperature is stabilized to prepare for caramel application. Now that the nougat segments are cooled, cut to precise dimensions, and cued in alignment on the conveyor system, the next phase in the Mars chocolate bar manufacturing process begins: the production and deposition of the caramel layer. This caramel is not a generic topping, it's one of the signature components that defines the textural and flavor contrast of a Mars bar. Creating this layer at scale requires a specialized process that integrates continuous cooking, emulsification, temperature control, and precision depositing, all engineered to work seamlessly within the speed and flow of a high-volume confectionery production line. The caramel used in Mars bars is made from a carefully balanced combination of sugar, glucose syrup, sweetened condensed milk or milk solids, and a specific blend of fats and emulsifiers. It's cooked to achieve a particular consistency, not too firm, not too runny, with a creamy chew that holds its shape during wrapping and storage, yet yields easily when bitten into. The production of caramel begins in a dedicated cooking area, separate from the nougat line, but synchronized with it to maintain constant throughput. All ingredients are stored in bulk near the cooking zone. Sugar and milk powders are gravity-fed from silos into high-shear premixes, while glucose syrup and fat are pumped in from temperature-controlled tanks. The emulsifiers, such as mono and diglycerides, are introduced through metering pumps in very small, tightly controlled amounts to help ensure smooth texture and fat-water dispersion. A water phase may also be introduced at the start to aid in initial dissolution and prevent localized overheating. The entire mixture is first blended in a jacketed stainless steel preheating tank, where it's brought to a uniform temperature of around 70 to 80 degrees Celsius. This pre-cooking stage ensures that all ingredients are fully homogenized before entering the main caramel cooker. From here, the caramel mix is pumped continuously into a vacuum caramel cooker, a specialized machine that allows rapid, even heating while removing excess water to control the final solid's content and viscosity. Vacuum caramel cookers work by reducing the internal pressure in the cooking chamber so that water boils off at a lower temperature. This is crucial to avoid burning the sugars or overcooking the milk solids, which could lead to bitter notes or textural instability. Inside the cooker, the mix is heated to between 115 degrees Celsius and 120 degrees Celsius. The target is to achieve a final water content of around 6 to 8%, with a sugar concentration of roughly 80 to 85 brix. Inline refractometers monitor this constantly, and the cooker adjusts residence time or heating level as needed to meet the spec. Once cooked, the caramel exits the cooker as a thick, glossy liquid with a rich golden brown hue. But before it can be applied to the nougat, it must be slightly cooled and tempered to a very specific range, typically between 45 degrees Celsius and 55 degrees Celsius. This cooling step stabilizes the caramel structure, allowing it to flow evenly during deposition without dripping or bleeding into the nougat layer. Cooling is performed in a jacketed holding tank equipped with slow-speed agitators that prevent crusting and keep the mixture homogeneous. With the caramel at the correct temperature, it's piped toward the depositing station. Here, the aligned nougat segments are conveyed under a continuous curtain-style depositor or a series of timed nozzles. Each piece receives a uniform layer of caramel, typically around 5 to 6 millimeters thick, depending on the final product specification. The depositor is precisely synchronized with the line speed, often using servo motors and optical sensors, so that each caramel stream lands squarely on the nougat block without overflow or excess. In higher speed lines, a pre-formed caramel sheet may be used instead. In this method, caramel is spread onto a separate cooling belt, allowed to set into a thin slab, and then laminated onto the nougat in one continuous motion using compression rollers. This technique allows better layer thickness control at very high production speeds and ensures cleaner edges for slicing. Once the caramel is applied, the dual layer bar now enters another cooling tunnel, usually a multi-zone refrigerated belt system that brings the caramel from 50 degrees Celsius down to just under 20 degrees Celsius. This cooling step must be gradual and controlled. Too rapid, and the caramel may contract unevenly, leading to separation from the nougat. Too slow, and it may remain sticky, interfering with the next step. Chocolate enrobing. During cooling, the layered bar is gently compressed by a roller to ensure adhesion between nougat and caramel. Then, it's passed through edge trimmers, which shave off the sides of the slab to produce perfectly square bars with clean, vertical sides. These trimmed edges are not wasted. They are collected via vacuum conveyors and reprocessed, either remelted or reformed, depending on factory protocol. The bar, now comprised of a cooled nougat base and a bonded caramel layer, is next cut into individual pieces using high-speed guillotine cutters. These are precision machines equipped with hardened stainless steel blades or ultrasonic cutting systems that minimize drag and preserve edge integrity. Each piece is exactly the length and width of a finished Mars bar, around 10 centimeters long and weighing roughly 51 to 57 grams, depending on the market. As the bars are cut, they are spaced out evenly using puck conveyors or lane dividers, aligning them perfectly for entry into the chocolate enrobing section. The temperature, moisture, and dimensional uniformity of each bar are verified by inline sensors and vision systems. Bars that are cracked, too short, or unevenly shaped are automatically diverted off the line for manual inspection or rework. At this stage, we transition into the enrobing process, the iconic step where each bar is coated in a smooth layer of Mars proprietary milk chocolate blend. This chocolate is stored in large tempering tanks, located just prior to the enrober. These tanks keep the chocolate at the ideal crystallization state, ensuring a glossy finish and firm snap after cooling. The chocolate used in Mars bars is a blend of cocoa liquor, cocoa butter, sugar, and milk solids, with added emulsifiers like soy lecithin to enhance flow properties. The tempered chocolate is pumped into the enrober, which is essentially a tunnel lined with a bottoming section to coat the base of each bar, and a curtain section to drape chocolate over the top and sides. Each Mars bar passes first over a shallow pool of chocolate to coat its underside, then directly beneath a flowing curtain that envelops the rest of the bar. A gentle stream of warm air is directed across the top to remove excess and create a rippled surface texture, a distinctive feature of the Mars bar. After enrobing, the bars are conveyed into the cooling tunnel, an extended refrigerated belt system approximately 20 to 30 meters in length. Inside, the environment is segmented into zones that gradually lower the temperature of the bars from around 32 degrees Celsius to 10 degrees Celsius. This staged cooling helps the cocoa butter in the chocolate crystallize properly, locking in the sheen and texture while avoiding fat bloom or streaks. Throughout this tunnel, air humidity is tightly controlled, generally under 50%, to prevent condensation on the chocolate. Dew point sensors and fans work in tandem with the refrigeration units to maintain a stable microclimate. The bars spend 5 to 8 minutes in this tunnel before emerging with fully set coatings, ready for packaging. As the cooled and finished bars exit the tunnel, they're fed into accumulation conveyors and grouped for wrapping. Each bar passes through a flow wrapping machine where printed film is unwound, formed into a sleeve, and sealed around the product. The wrapper is then crimp sealed on both ends and trimmed. These wrapping machines can process hundreds of bars per minute, and each wrapped bar is weighed and scanned before being discharged onto final packing belts. At this point, the product is visually indistinguishable from the Mars bar found on store shelves, but the process is still not finished. The next stage involves secondary packaging, grouping bars into boxes, cartons, and shipping trays, and preparing them for distribution. As the fully formed, enrobed, and cooled Mars bars make their way off the production line, they enter the final stages of the factory process, beginning with high-speed wrapping and continuing through automated boxing, palletization, storage, and outbound logistics. These downstream systems are critical not just for protection and presentation of the product, but also for ensuring traceability, quality retention, and supply chain synchronization. While the visible production, the mixing, cooking, cutting, and coating is complete, the final packaging and handling stages are no less intricate, built on robotics, data systems, and industrial automation designed to manage millions of units every day. The first stop is the wrapping station. Here, each Mars bar moves along the conveyor belt in single file toward the flow wrapping machine. This machine feeds a continuous roll of printed film into a series of folding arms and sealing jaws. As each bar enters, the film wraps around it in a tight, tubular sleeve, and heated crimp jaws at either end form the back seal and the end seals simultaneously. The temperature of these jaws is maintained within a few degrees of the sealing material's activation point to ensure strong, clean closures without melting or burning the film. Mars uses multi-layered packaging films that are designed not only to provide barrier protection against oxygen and moisture, but also to deliver the tactile feel and gloss that customers expect from premium chocolate packaging. The inner layer is typically a heat-sealable polymer. The middle layer may include aluminum or metallized PET for barrier properties. And the outer layer is printed with brand artwork and product information. The printed designs are registered with high-precision sensors, so every bar's logo aligns perfectly. Any misregistered wrapper is automatically detected and rejected by an optical scanner system. Once sealed, the wrapped bar passes over a check weigher, an in-motion scale that ensures the final packaged weight is within tolerance. If a bar is over or underweight, even by a gram, it's automatically diverted. Next, each unit is passed under a metal detector, which checks for any possible foreign objects that could have entered the bar during earlier processing stages. These systems are highly sensitive and calibrated daily with test pieces. Some plants also employ X-ray machines that detect not just metal, but dense, non-metallic contaminants, such as glass or stone. Bars that pass all inspections continue down the conveyor toward the cartoning line. Depending on the intended retail format, bars may be grouped into multi-packs, retail-ready trays, or shipping cartons. Robotic arms, or high-speed diverters, organize the flow of individual bars into stacks, 4, 6, 10, or 12 bars wide, and gently push them into pre-folded cardboard sleeves or boxes. These secondary packages are then sealed using hot melt glue or tuck-in flaps, depending on market requirements. Each package receives a printed label with batch number, timestamp, factory ID, and possibly a QR code for inventory tracking. From here, boxed products are routed to the palletizing station. Robotic palletizers pick up full cases using vacuum grippers or mechanical arms and stack them on wooden or plastic pallets in precise formations. Each layer is arranged to optimize space, balance, and load stability. Between layers, some systems add cardboard slips or corner protectors for reinforcement. Once the pallet reaches its programmed height, typically 1.6 to 1.8 meters, it's wrapped in stretch film by an automatic wrapper, which rotates the pallet while dispensing the film under tension to secure the load. The wrapped pallets are then fitted with pallet labels that include the SKU, total unit count, gross weight, destination code, and a unique identifier that ties back to the factory's internal tracking system. These labels are printed by thermal printers and verified by barcode scanners before the pallets are cleared to enter the finished goods warehouse. Before we go further, it's important to recognize the role of Mars factory control systems in managing this entire post-production phase. All equipment is integrated into a centralized manufacturing execution system, MES, that tracks every product in real time. Each bar, box, and pallet carries data embedded in barcodes or RFID tags about when it was made, on which line, using which ingredients, and under what conditions. This traceability is a cornerstone of food safety compliance and internal quality assurance. The finished goods warehouse is where the newly palletized bars await shipment. This warehouse is fully climate controlled to maintain optimal temperature and humidity for chocolate storage. Temperature is held at 18 to 20 degrees Celsius with relative humidity below 55% to prevent bloom, melting, or texture changes. Air circulation systems keep temperature consistent throughout the space, while insulation and vapor barriers prevent external fluctuations from impacting internal conditions. Inventory in the warehouse is managed using automated guided vehicles, AGVs, or forklifts equipped with real-time location systems. When pallets are stored, they're scanned into the warehouse management system and placed according to distribution priority. High turnover products are stored closer to the shipping bays, while seasonal or export variants may be stored deeper in the racking system. The storage time for any batch is typically less than a week, as Mars factories operate on just-in-time logistics, pushing product out daily to meet distributor orders. When shipments are requested, the warehouse team receives a digital pick list. AGVs or operators retrieve the designated pallets, verify them via handheld scanners, and stage them at the outbound docks. Before loading, each shipment is inspected to ensure it matches the order specification, is within temperature tolerance, and has intact pallet wrapping. Refrigerated or climate-controlled trucks are often used for long-distance shipments or deliveries to regions with high ambient temperatures. Loading is done using dock levelers and roller systems to ensure smooth movement and prevent tipping. During transit, temperature loggers accompany the shipments, recording data at set intervals. These loggers are checked upon delivery, and if any deviation from the acceptable range is detected, the shipment may be flagged for inspection or rejection. Mars also monitors customer feedback, market audits, and in-store quality surveys. Samples of each production lot are retained in climate-controlled storage at the factory for shelf life testing. These retained samples are periodically tested for appearance, taste, texture, and microbiological stability over the course of months, ensuring that every production protocol performs as expected long after the product has left the plant. Parallel to all of this is a dedicated quality control laboratory. Here, daily production samples are subjected to physical and chemical analysis. Moisture content, fat content, sugar crystallinity, pH, and emulsion stability are checked using instruments like Carl Fisher titrators, differential scanning calorimeters, and viscometers. Sensory panels trained in Mars' specific flavor and texture profiles evaluate samples for aroma, mouthfeel, and aftertaste. Auditors regularly conduct surprise inspections, testing product against regulatory standards in every region the factory exports to. Some facilities even run accelerated aging chambers, simulating 6 months of shelf life in a few weeks using controlled temperature and humidity cycling. This allows the company to predict how new packaging or ingredient changes may impact long-term stability before releasing them to the market. Within the final layers of Mars chocolate bar manufacturing process lies an often unseen, yet deeply critical infrastructure dedicated to innovation, iteration, and global standardization. While the production lines are optimized for high-speed consistency, behind the scenes, the company operates pilot plants and R&D laboratories, where new formulations, production methods, and equipment calibrations are continuously tested, refined, and validated before they're deployed across global facilities. Every Mars chocolate bar, regardless of where it is produced, in the United States, the United Kingdom, or other licensed manufacturing hubs, must adhere to an extremely narrow window of variation. This means the bars must look, taste, feel, and behave identically, despite being produced in plants thousands of kilometers apart. Achieving this demands extensive process documentation, real-time data comparison, and coordinated updates to recipes and equipment settings across all sites. Pilot plants, often located adjacent to main production facilities, house miniature versions of the full-scale equipment, scaled-down mixers, depositors, tempering tanks, and enrobers, used not just for prototyping new flavors or bar formats, but also for stress testing ingredient substitutions, adjusting for new cocoa sources, or modifying emulsifier levels in response to regional ingredient availability or regulation. A new Mars bar variant, such as one with an added layer of cookie or a salted caramel flavor, may go through dozens of test batches before scaling. Each trial is evaluated not just for consumer preference, but for how it performs on actual equipment. Does the caramel spread at the correct rate on moving belts? Does it maintain form through the cooling tunnel? Does the chocolate enrobe correctly without altering crystallization time? These questions are answered with data from test runs that are digitally logged and used to generate predictive models before any large-scale production begins. Digital twins, virtual simulations of real production environments, are increasingly being used in these trials. These tools model fluid dynamics, thermal behavior, and mechanical stress on ingredients during cooking, cooling, and transport. They allow engineers to simulate a dozen line changes without touching a single piece of physical equipment, drastically accelerating the pace of safe innovation. Once a new process is approved, Mars Global Standardization Team prepares comprehensive change packs, which include updated process parameters, safety protocols, ingredient specs, equipment calibration charts, and software updates. These packs are then distributed to all regional manufacturing hubs, often followed by remote training sessions or on-site visits to ensure implementation is seamless. This global coordination ensures that whether you open a Mars bar in Chicago, Sydney, or Madrid, the experience is identical, down to the snap of the chocolate, the elasticity of the caramel, and the melt rate of the nougat. In a modern Oreo manufacturing facility, key dry ingredients are delivered in bulk, often by rail cars or food-grade trucks, and are pneumatically conveyed into large storage silos made of stainless steel or epoxy-lined carbon steel. These silos are sealed from air and moisture and are connected to the factory's central control system. The main dry ingredients include unbleached, enriched wheat flour, processed cocoa powder, granulated sugar, and minor dry components like baking soda and salt. Each of these materials is handled in its own silo or hopper, and automated augers or vibratory feeders dispense precise quantities into batch weighing hoppers. These hoppers sit on load cells, sensitive scales that can measure down to a fraction of a gram. This is essential because the correct ratio of flour to cocoa to sugar directly affects not only the flavor, but also how the dough behaves under pressure during molding. If the cocoa content is even slightly too high, for instance, the dough may become too brittle and crack during forming. If it's too low, the wafers may bake up too soft, losing the crisp snap that defines an Oreo. Once the dry materials are batched, They are conveyed into a pre-mixing chamber. At this stage, powdered ingredients are briefly tumbled together to ensure initial homogeneity before liquids are added. Then it's time for the liquid components to enter the system. These include vegetable shortening, often a blend of palm and canola oil, along with a sugar syrup or glucose solution, invert sugar, lecithin, and vanillin or other flavoring agents. The fats and liquids are stored in temperature-controlled tanks and are metered into the mixer through heated pipes. The temperature of the fats is critical. Too cold and they won't disperse evenly. Too hot and they could melt too aggressively, breaking down the emulsion and affecting dough integrity. All of these components are combined in large jacketed horizontal mixers or double sigma arm batch mixers. These mixers are chosen for their ability to handle heavy, cohesive doughs while still ensuring thorough dispersion. Inside the mixer, paddles or blades knead the dough continuously, folding and stretching it to develop a uniform texture. The mixer operates under a specific time and speed profile, starting slow to incorporate the dry and wet components, then increasing speed to blend, then finishing with a gentle knead to avoid overworking the dough. The goal here is a dough that's soft but not sticky, cohesive but not tough. Sensors inside the mixing chamber monitor temperature and torque, two key indicators of dough readiness. If the dough becomes too warm from friction, it can become greasy and difficult to form clean edges in the molding machines. If it's undermixed, the ingredients won't be uniformly distributed, and inconsistencies in cookie size, color, and bake profile will result later on. Once the dough reaches its target specifications, it's discharged from the mixer through a hydraulically controlled trapdoor at the base of the mixing tank. The dough falls into a dough transport system, typically a set of conveyors or troughs lined with non-stick materials like Teflon or food-grade UHMW polyethylene. At this stage, the dough may still be slightly warm, around 30 degrees Celsius to 35 degrees Celsius, and has a dense, matte appearance with a strong cocoa aroma. Before moving to the forming machines, the dough must undergo a resting period in certain operations. This allows the flour to fully hydrate and any residual gases or trapped air to escape. In high-speed production environments, however, this rest period may be minimized or skipped altogether if the formulation is optimized for immediate processing. This completes the initial phase: ingredient intake, formulation, mixing, and dough discharge. Each step up to this point is carefully controlled by recipe management software that ensures no human error can affect batch consistency. Recipe locks, scanner-based operator identification, and redundant scale verification ensure each batch of Oreo wafer dough is made precisely to the specifications required to perform flawlessly in the next stage of the journey: shaping and embossing. Now that the chocolate wafer dough has been prepared with absolute precision, measured, mixed, and conditioned, it moves into one of the most visually iconic and mechanically fascinating phases in the Oreo production line: forming and molding. This step takes the dense, cocoa-rich dough and transforms it into thousands of uniformly sized, detailed cookie wafers, each embossed with the distinctive Oreo pattern. This is not simply cutting shapes out of dough, it's a highly engineered, high-speed process where consistency in shape, thickness, and surface detail must be maintained across millions of units every day. The freshly prepared dough is conveyed to a hopper positioned above a sheeter. This sheeter is a wide, stainless steel roller assembly that flattens the dough into a uniform sheet of specific thickness. The dough moves between a set of rollers, typically 2 or more steel cylinders calibrated to exact tolerances that compress it to the target height. For Oreo wafers, the final sheet is quite thin, often around 3 to 4 millimeters, with a consistent density and moisture distribution. Getting this thickness right is critical. If the sheet is too thick, the cookie may not bake evenly or could become too brittle. Too thin, and the cookies may crack, burn, or crumble during sandwiching. Sensors measure the thickness of the sheet continuously using laser or ultrasonic gauges. If deviations are detected, servo-driven actuators automatically adjust roller spacing to maintain precision. The sheeter also includes edge trimmers, small motorized blades that cut off uneven or frayed edges of the dough sheet to keep the line uniform. The trimmed edges are collected by a scrap recovery system and reintroduced into the mixing system, minimizing waste without compromising freshness or quality. Once the dough sheet is perfected, it enters the rotary molder. This machine is central to the Oreo brand's identity, as it forms the shape, size, and embossed design of each cookie wafer. The rotary molder consists of two primary components, a rotating die roller and a pressure roller. The die roller is a cylindrical drum engraved with multiple cavities, each one precisely carved with the Oreo design. These cavities aren't just cosmetic. Their depth and contour dictate the final relief of the cookie surface. As the dough sheet passes between the die roller and pressure roller, each cavity punches into the dough, compressing it into shape and imprinting the Oreo design. The pressure roller, covered in food-safe rubber or polymer, pushes the dough up into the die cavities, ensuring a clean, complete mold. As the die drum continues rotating, the shaped wafers are extracted by a combination of mechanical pushes and vacuum assist systems, which gently remove the cookies from the cavities without smudging the design. These freshly molded cookie wafers are then transferred onto a wide mesh conveyor belt in a continuous, uninterrupted line. Each wafer is spaced evenly to allow for proper airflow in the next phase, baking. Meanwhile, the excess dough surrounding the cutouts, known as webbing, is carefully separated and sent back through the scrap system. This recovery loop is highly efficient, capturing nearly 100% of the unused dough and returning it to the mixer via chilled transport belts. To ensure product consistency, reworked dough is blended at a fixed percentage into fresh dough, preventing any changes in texture, flavor, or moisture that might result from over-processing. As the line of uniform, molded Oreo wafers advances, they approach the baking tunnel, one of the most thermodynamically sophisticated parts of the facility. The tunnel oven is a massive structure, often exceeding 30 meters in length, segmented into multiple temperature-controlled zones. Each zone is precisely tuned to manage the gradual dehydration and expansion of the cookie, ensuring even baking from edge to center. The ovens use convection, conduction, and in some cases, radiant heat, depending on the equipment manufacturer and regional factory specifications. The cookie wafers bake as they travel slowly through the tunnel, typically for a duration of 4 to 6 minutes. Conveyor speed, airflow rate, and internal oven temperatures are continuously adjusted via programmable logic controllers that interface with sensors monitoring internal humidity, surface temperature, and even color of the baking cookies using infrared imaging systems. The target bake is one where the cookie becomes crisp and fully set while retaining a slight moisture gradient at its core, enough to ensure it sandwiches cleanly without shattering, and holds up in milk without becoming soggy too quickly. Another crucial parameter monitored at this stage is cookie spread and diameter. Because the molded wafers expand slightly as they bake, their final size must fall within a fraction of a millimeter to ensure they'll match perfectly with their paired half during sandwiching. Edge blowout, where cookies develop uneven bulges or bubbles, is prevented by careful control of initial dough temperature, mold compression depth, and oven humidity during the first baking phase. As the cookies exit the oven, they are immediately passed through a staged cooling system. This phase is designed to gently bring the cookies from their internal post-bake temperature of roughly 160 degrees Celsius down to ambient room temperature. Cooling too quickly can cause the wafers to crack, warp, or experience checking, tiny surface fractures that affect aesthetics and structural integrity. To avoid this, the conveyor slowly moves the wafers through a series of cooling zones with progressively decreasing airflow temperatures. High-volume fans push filtered, dehumidified air over the wafers in a cross-flow pattern that cools them evenly on all sides. By the time the wafers reach the end of the cooling tunnel, they are firm, crisp, and at a stable moisture level, typically around 1.5% to 2%. This ensures maximum shelf life, a satisfying crunch, and ideal compatibility with the creme filling in the next phase of production. They are now ready for alignment and pairing. Wafers are automatically aligned into dual streams using diverters and channeling guides. Conveyor belts equipped with vision systems scan for defects such as missing embossing, chips, discoloration, or breakage. These systems use high-speed cameras and AI-assisted pattern recognition to detect any imperfections in milliseconds. Rejected cookies are diverted to a waste collection hopper, and approved wafers continue forward to the sandwiching stage. With the Oreo chocolate wafer cookies fully formed, baked, and cooled, the production line now transitions into one of the most iconic and mechanically synchronized parts of the process: sandwiching. This stage involves the precise alignment of two delicate wafer halves around a carefully deposited swirl of creme filling, forming the complete Oreo cookie as we know it. What may seem like a simple task, placing filling between two cookies, is in fact a highly controlled and technically advanced process that prioritizes speed, accuracy, hygiene, and product consistency. The cooled wafers arrive at the sandwiching station via dual-lane conveyors that separate and feed cookies into two different orientations: bottom wafers and top wafers. The bottom wafers are destined to receive the cream filling, while the top wafers are held back momentarily, synchronized to arrive just as the filling has been deposited. Vision-guided pick-and-place arms or mechanical guides ensure that each cookie is properly positioned and oriented with the embossed design facing upward, especially important for branded recognition in the final presentation. The placement needs to be exact. Even a slight misalignment could result in uneven sandwiching or a crooked creme center, which would be rejected downstream. At the heart of the sandwiching line is the creme depositor. This component is engineered to dispense a precise amount of creme onto the center of each bottom wafer. The creme filling itself has been prepared earlier in the process and is stored in stainless steel holding tanks near the sandwiching line. The base creme is a blend of vegetable shortening, powdered sugar, and natural or artificial flavorings, aerated to achieve a smooth and creamy texture. It is kept at a controlled temperature, typically between 25 degrees Celsius and 30 degrees Celsius, to maintain flow consistency without being too runny or too firm. The creme is pumped into the depositor through a jacketed delivery line, which maintains temperature and prevents any hardening or separation. Inside the depositor, a rotary valve system or piston-driven nozzles release measured quantities of filling in circular swirls directly onto each passing wafer. The target deposition amount is extremely precise, usually around 3 grams per cookie for the original Oreo. For double stuff, the system is calibrated to deliver twice that volume, and the depositor nozzle height is adjusted accordingly to accommodate the larger swirl. The deposition speed is synchronized with the conveyor, meaning each swirl is deposited while the bottom wafer is in motion. To maintain consistent swirl shapes, the nozzle spins at a high RPM as it dispenses the cream. Sensors and imaging software track swirl size, height, and position. If the deposit strays from the central zone or falls outside weight tolerances, that cookie is automatically flagged and diverted. These sensors run continuously, sampling thousands of cookies per minute with extremely tight thresholds for variance. Once the creme is in place, the top wafer is gently placed onto the swirl. This is done by an overhead transfer arm or drop chute designed to lower each top cookie into place with just enough pressure to make contact without squashing the filling. The timing here is critical. Placing the top wafer too early could create smearing or incomplete adhesion, while placing it too late could allow the creme to set and result in a loosely held sandwich. Once the two halves make contact, a calibrated compression roller or paddle gently presses them together to create a uniform sandwich with a visible, even creme edge. The newly assembled Oreo cookies are then conveyed forward to undergo another round of quality inspection. At this stage, high-speed vision systems again scan for defects. These include cracked or broken wafers, misaligned sandwiches, off-center cream, or excess filling that has oozed out past the edges. Cookies that fail to meet standards are ejected via pneumatic pushers or retractable gates, landing in separate bins for non-conforming product. These rejected cookies are either discarded or recycled depending on factory policies and whether they passed earlier food safety checks. The good cookies move on to the next major phase, cooling and setting. Even though the creme filling is solid at room temperature, the act of depositing and sandwiching generates residual warmth, and the filling remains somewhat malleable for several minutes. To stabilize the sandwich structure and ensure long-term integrity during packaging and shipping, the cookies are passed through a controlled cooling tunnel. This tunnel gradually brings the product's temperature down to a stable point, typically just below ambient, which firms up the cream and locks in the sandwich's structural cohesion. As cookies exit the cooling tunnel, they are directed toward the packaging line. Here, the cookies are grouped and arranged into stacks or rows depending on the intended package format, whether it's a classic tray-style retail pack, a resealable pouch, a single-serving sleeve, or a multi-pack unit. For traditional packs, the cookies are guided into channels that group them into stacks, typically of 3 or more, which are then lowered into thermoformed plastic trays by robotic pick-and-place units. These trays help protect the cookies from damage and keep them organized for end-user convenience. Parallel to this, packaging film, pre-printed with branding, nutritional labels, and product information, is unwound from large rolls and fed into a form-fill seal machine. As the cookie-filled trays pass through the machine, the film is wrapped around the product, heat-sealed on all sides, and trimmed to size. Oxygen scavengers or desiccants may be inserted for freshness in some markets, depending on climate and shelf life requirements. For resealable packs, a Ziploc or peel-back adhesive strip is applied as part of the film sealing process, ensuring that consumers can open and close the package without reducing freshness. Each package unit is printed with a lot number, manufacturing date, facility code, and expiration date using high-speed thermal inkjet or laser printers. These codes enable full traceability and are cross-referenced with the production batch data stored in the factory's ERP system. From mixing and molding to creme filling and sealing, every step of the process can be traced back to specific machines, operators, shift schedules, and ingredient batches, an essential feature for food safety compliance and recall readiness. Once sealed, packages are conveyed to automated case packers. Here, robotic arms load the wrapped units into corrugated cardboard cartons, which are then glued or taped shut. These cartons are palletized according to preset patterns that optimize load stability and cube efficiency for shipping. Pallets are wrapped with stretch film, labeled with shipping barcodes and inventory data, and routed to the warehouse staging area. At this point, the Oreo cookies have completed their physical transformation from separate cocoa wafers and creme filling into a polished, fully packaged, ready-to-ship product. But before they leave the factory, they undergo a final quality audit. Samples from each batch are pulled from the finished goods line and tested by in-house sensory panels and laboratory staff. Taste, texture, aroma, appearance, and moisture content are evaluated to ensure that the product not only looks perfect, but delivers the consistent flavor and mouthfeel that Oreo is known for. Moisture levels are especially critical. Too high, and the cookie can lose its crispness during storage. Too low, and it can become brittle or stale. Texture analyzers apply mechanical pressure to the cookies to evaluate crunch resistance and breaking force, while gas chromatography is used to verify flavor compound profiles. Packaging integrity tests include drop tests, seal strength verification, and temperature cycling simulations that mimic transport and storage conditions across various markets. Once these final inspections are passed, the cookies are released for distribution. Pallets are loaded into climate-controlled trucks or containers, routed through regional distribution centers, and ultimately arrive at retail outlets, vending networks, or direct-to-consumer channels. With the Oreo cookie now fully assembled, inspected, packaged, and palletized, the final phase of the in-factory process is dedicated to the logistics, storage, inventory control, and outbound quality assurance systems that prepare the product for global distribution. While it may seem like the technical complexity is behind us, this stage involves its own set of sophisticated workflows designed to ensure that every package remains pristine, traceable, and shelf-stable for months after production, regardless of whether it ends up in a small, rural convenience store or a high-volume urban supermarket. The finished pallets of Oreos are moved from the end-of-line palletizing systems into a dedicated finished goods warehouse. This space is part of the factory complex, but isolated from production to prevent cross-contamination and maintain temperature and humidity stability. Oreo cookies, especially those with creme fillings, are highly sensitive to environmental changes. Excessive heat can soften the filling or compromise the packaging seal, while high humidity can cause moisture migration into the wafer, leading to loss of crispness. To combat these risks, the warehouse is maintained at a tightly regulated temperature, typically between 18 degrees Celsius and 22 degrees Celsius, with relative humidity kept under 50%. The facility is segmented into climate zones for different packaging formats, with certain areas reserved for international shipments that may require added humidity resistance or longer storage durations. Air handlers, industrial-grade dehumidifiers, and air filtration systems constantly regulate and cycle the air to maintain these parameters. Even the lighting systems are designed to minimize UV exposure, which could, over time, degrade packaging ink or food contact films. Once inside the warehouse, each pallet is scanned and logged into a warehouse management system. This system is fully integrated with the factory's enterprise resource planning software and allows operators to track not only where each pallet is stored, but exactly what production line, time, and ingredient lot was used to produce its contents. Each pallet label includes a unique serial number, barcode, and QR code that links to this full production history. This traceability is essential not just for internal logistics, but also for compliance with food safety regulations around the world, which require manufacturers to be able to track every product from raw ingredient to final point of sale. The WMS automatically arranges pallets by product type, batch date, and destination. Those scheduled for export may be routed to a separate staging zone where they will be checked for compliance with international packaging laws. Different markets may require translated labels, adjusted nutritional formats, or modified lot codes. Some export destinations also require additional tests, such as microbial swabs or accelerated shelf life sampling, to meet foreign government regulations. These are performed in an adjacent quality control annex, and only upon clearance are these pallets released to outbound logistics. Before any Oreo shipment leaves the facility, it undergoes a final visual inspection for physical damage to packaging, tamper seals, and box integrity. Any visible damage may indicate mishandling during internal transit or weak spots in pallet stability. Operators are trained to look for warped trays, compromised seals, or even small tears in the flow wrap film that could affect product freshness. Should any defect be discovered, that pallet is held for secondary inspection, and depending on severity, it may be repackaged or scrapped entirely. At this point, logistics coordinators use automated routing systems to schedule outbound shipments. These systems factor in geographic location, delivery deadlines, climate conditions, and truck availability. For example, shipments bound for warmer climates during the summer may be prioritized for insulated or refrigerated trucks to prevent the creme from softening. Long-haul shipments may be routed through distribution centers that offer cross-docking or climate-controlled storage to preserve product quality along the supply chain. The loading dock itself is operated with precision. Trucks arriving at the facility must be cleaned, inspected, and approved before any Oreo products are loaded. This includes visual inspection for pests, residue from prior shipments, and confirmation that the trailer temperature is within specification. Only after a truck passes these inspections does the facility open the dock door and begin the loading sequence. Robotic forklifts or human operators load the pallets according to pre-planned diagrams that ensure weight is evenly distributed and product is easily accessible at the destination. Each shipment is logged with time, driver ID, carrier information, route ID, and estimated delivery window. Once loaded, trucks are sealed with tamper-evident locks and dispatched with digital shipping documents, including delivery confirmations and scanned QR codes for receiving teams. The WMS updates the ERP system in real time, closing the inventory loop and marking the batch as shipped. This inventory and logistics traceability is crucial for meeting compliance with global food safety standards like the Global Food Safety Initiative, hazard analysis, and critical control points, and ISO 22000. Even after the Oreo product leaves the plant, the factory remains connected to its life cycle through digital feedback systems. Retailers and distributors have access to portal-based interfaces where they can report damages, delayed deliveries, or unexpected inventory issues. Returned products are scanned upon arrival at reverse logistics zones where factory staff investigate issues, analyze production records, and determine root causes. In cases where errors are found, such as premature staleness, flavor imbalance, or packaging failure, continuous improvement protocols are triggered to address the upstream causes. While these systems function to protect the product, they also feed into a broader factory goal: performance analytics and continuous optimization. The data from every shipment, temperature logs, shipping duration, breakage rates, seal integrity, and even consumer complaints is compiled into dashboards reviewed weekly by production leads, QA managers, and logistics coordinators. These dashboards enable the factory team to track KPIs like OTIF, defect per million rates, inventory turnover, spoilage reduction, and carbon footprint per pallet. Some Oreo plants are moving even further towards sustainability at this stage of production. Cardboard shipping boxes are made with recycled content and are themselves fully recyclable. Pallet wrap films are being downgauged or replaced with biodegradable alternatives. Facilities are experimenting with hybrid electric fleet partnerships or rail transport instead of trucks to reduce emissions. In select markets, even the plastic trays inside Oreo packs have been redesigned for recyclability, and clear labels now inform consumers on proper disposal. Chocolate begins its life not in the factory, but on the tropical cacao farms that line the equator. These farms are located in countries across West Africa, Central and South America, and Southeast Asia, with Ivory Coast and Ghana among the world's top producers. The climate in these regions, hot, humid, and with rich, well-draining soil, is essential for the cultivation of Theobroma cacao, the tree that produces cacao pods. Each pod contains 20 to 50 seeds, known as cacao beans, surrounded by a sweet, pulpy, white fruit. These beans are the raw foundation of all chocolate products. The cacao harvest is entirely manual. Farmers use machetes or curved knives attached to long poles to carefully cut ripe pods from the trees without damaging the branches. A single mature tree may produce between 20 and 30 pods per year, and since cacao does not ripen all at once, harvesting occurs continuously over several months. Once harvested, the pods are collected in piles and opened by hand using machetes. The beans, still coated in sticky white pulp, are scooped out and prepared for fermentation, the first transformative step in the chocolate making process. Fermentation typically occurs on the farm or at centralized collection centers. Though it might sound like a simple resting period, fermentation is a critical and highly sensitive step that chemically alters the beans and begins to develop the flavor precursors of chocolate. Beans are placed in shallow, slatted wooden boxes or piled into heaps and covered with banana leaves. This environment encourages the growth of natural yeasts and bacteria that convert sugars in the pulp into alcohol and acids. As the temperature rises, often reaching 45 to 50 degrees Celsius, the bean's internal structure changes. Enzymes are activated, cell walls are broken down, and bitter polyphenols begin to transform into the complex flavor compounds that will later give chocolate its signature taste. Fermentation typically lasts 5 to 7 days, during which the beans are turned or mixed once or twice a day to ensure even microbial activity and oxygenation. This step is closely monitored, as under-fermentation leads to bland or vegetal flavors, while over-fermentation can introduce off notes like mold, vinegar, or excessive bitterness. Many large chocolate manufacturers, even though they don't ferment beans on site, have established quality programs with their cacao suppliers, training them in fermentation control, and even requiring on-site testing of pH and temperature during the process. Once fermentation is complete, the beans are spread out to dry. Drying can be done on large tarpaulins, bamboo mats, or raised wooden platforms under the sun. Industrial cacao processors often prefer sun drying, which can take 5 to 10 days, as it produces cleaner, more natural flavor profiles. During drying, the beans are turned regularly to ensure even moisture loss. The goal is to reduce the moisture content to around 6%, 7%, a safe level that prevents mold and microbial growth during storage and transport. At this point, the beans are still covered in their thin, brittle shells and have taken on a dark brown color, with their signature earthy, chocolatey aroma starting to develop. The beans are carefully bagged in burlap sacks, usually 60 to 65 kilograms per bag, and labeled with origin information including country, region, farm or co-op, and processing dates. These bags are then consolidated for export. Exporting cacao beans requires extreme care and logistics planning. Moisture, heat, and exposure to foreign odors can degrade the beans before they even reach the factory. To prevent spoilage, the sacks are loaded into dry, ventilated shipping containers, often lined with insulating material or desiccant packs to control humidity. During long overseas shipments, particularly by sea freight, the cargo is monitored using data loggers that track temperature and humidity. If the beans are exposed to extreme conditions, entire shipments can be rejected by the receiving chocolate manufacturer. When the beans arrive at the chocolate factory, usually located in Europe, North America, or Asia, they undergo a rigorous intake and inspection process. This is where industrial chocolate production truly begins. First, the bags are unloaded into a receiving area, where samples are drawn from each lot and taken to the quality control lab. Here, technicians measure moisture content, check for mold or insect damage, and grade the beans based on size, color, and cut tests. Cut tests involve slicing a sample of beans lengthwise and examining the cross-section. Properly fermented beans will have a uniform, slightly purplish interior with no signs of germination or off colors. Beans that meet the manufacturer's standards are then approved for processing. The sacks are emptied into large hoppers that feed the cleaning and pre-processing line. At this point, the factory begins to function much like a grain mill, sorting, cleaning, and prepping the raw material for transformation. The first stage is mechanical cleaning. The beans pass through vibrating screens and air jets that remove sticks, stones, dust, string, and other foreign materials. Magnetic separators remove any stray metal particles picked up during harvest or shipping. After cleaning, the beans are often sorted by size. This is an optional step, but many high-end chocolate makers insist on sorting to ensure that beans of uniform size are roasted together. Uneven roasting is a major risk if large and small beans are mixed, as the small beans may burn while the larger ones under-roast. Before roasting, the factory may also conduct a dehumidification step, particularly if the beans arrived slightly above target moisture. Large rotary dryers or low-temperature ovens are used to bring the beans into precise moisture range, often 5%, 6%, to prepare for optimal roast conditions. This is all monitored through programmable logic controllers that track time, temperature, airflow rate, and moisture loss in real time. With the cacao beans now thoroughly cleaned, dried to precise moisture levels, sorted by size, and passed through rigorous quality inspections, the chocolate production process enters one of its most transformative and delicate phases: roasting. This step marks the moment when raw agricultural product begins to develop the hallmark sensory properties of finished chocolate: aroma, depth, bitterness, sweetness, and complexity. Far from being a simple baking process, industrial chocolate roasting is a finely tuned science that must balance heat, time, air circulation, and even bean origin to unlock the flavor potential locked within the bean's cellular structure. The roasted profile of chocolate is not one size fits all. It varies greatly depending on the origin of the beans, the desired flavor profile of the final product, and the style of chocolate being produced, whether it's milk, dark, or even single origin specialty bars. As such, chocolate factories have roasting protocols tailored to each bean variety and product type. These protocols are logged as roast profiles, charts that map temperature over time, often broken into phases: drying, browning, and development. Each phase requires precise thermal input and airflow to extract the right flavors without burning or flattening the bean. Industrial chocolate factories use several types of roasters depending on scale and product goals. The most common are batch drum roasters and continuous roasters. Batch drum roasters, similar in design to coffee roasters but much larger, feature a rotating cylindrical drum made from stainless steel. Beans are loaded into the drum, which rotates over direct or indirect heat, with hot air circulated through the drum chamber. Temperature sensors embedded in the drum monitor the bean mass, ambient air, and exhaust temperatures simultaneously. Factory operators can adjust drum speed, airflow rate, and burner intensity through PLC-controlled interfaces to manage the roast curve. Roasting typically begins at a lower temperature, around 100 degrees Celsius, to drive off any remaining surface moisture. This is the drying phase and usually lasts for 5 to 10 minutes. The beans then enter the browning phase, where the Maillard reaction begins. This is the chemical process that causes amino acids and reducing sugars in the beans to recombine and form hundreds of flavor compounds: nutty, roasted, caramelized, and acidic notes that are essential for chocolate's complexity. This phase is carefully controlled, usually taking another 10 to 15 minutes, with bean temperatures rising to 120-140 degrees Celsius. The final stage of roasting is known as development, or the finishing phase. Here, the beans are brought to their final internal temperature, typically between 135 degrees Celsius and 150 degrees Celsius, depending on the desired flavor profile. This phase is brief, often just 2 to 5 minutes, but it's critically important. Too little development, and the flavor may be grassy or underwhelming. Too much, and the chocolate may taste burnt, acrid, or flat. Advanced factories use real-time infrared cameras and bean temperature probes to monitor this phase with incredible accuracy, sometimes recording temperatures at 1-second intervals. After roasting, the beans must be cooled quickly to halt the cooking process. This is usually achieved in a dedicated cooling drum or tray system, where ambient or chilled air is blown across the beans using high-speed fans. Cooling not only stops the roast, but it also firms up the bean shell and prevents steam buildup, which could cause condensation or spoilage during storage. At this point, the beans are dark brown, fragrant, and brittle, but they still contain their outer shells, a thin, papery husk that must be removed to access the valuable interior, the cacao nib. The next phase is known as winnowing. Winnowing is a mechanical process that cracks the beans open and separates the lightweight shells from the dense nibs using a combination of crushing and air classification. In a large-scale chocolate factory, beans are first passed through a pre-cracker or roll crusher, which breaks them into fragments of varying size. The cracked mixture is then fed into a winnowing chamber, often a series of vertical air columns or vibrating conveyor belts, where calibrated air jets or suction systems separate the heavier nibs from the lighter shells. The airflow is precisely tuned so that the nibs fall to the bottom collection bins while the husks are drawn upward into separate waste hoppers. The result is a batch of pure cacao nibs, dark, rich, and packed with flavor and cocoa solids. These nibs are now ready to be transformed into chocolate liquor, not an alcoholic beverage, but a thick, paste-like substance made from finely ground cacao nibs. This is where the chocolate truly begins to take shape. To produce liquor, the nibs are passed through industrial grinders known as pre-refiners or impact mills. These machines use either rotating steel blades or stone rollers to shear the nibs into smaller and smaller particles. As the nibs are ground, frictional heat causes the cocoa butter inside to melt. This transforms the mixture from a coarse, gritty powder into a flowing paste with a smooth, velvety texture. The grinding process typically reduces particle size to around 80 to 100 microns during this first stage. From here, the liquor is either held in heated tanks for further processing or sent directly to the next grinding phase, refining. Refining is the step where particle size is further reduced to achieve the smooth mouthfeel expected from high-quality chocolate. This is performed using 5-roll refiners or ball mills. 5-roll refiners consist of 5 horizontally stacked steel rollers, each rotating at a different speed. The chocolate liquor is fed into the gap between the rollers, which progressively shear the particles down to between 15 and 25 microns. At this size, individual cocoa and sugar particles are too small for the tongue to detect, giving chocolate its creamy texture. In factories producing sweetened chocolate, sugar is added during this refining phase. The sugar, already pre-milled to ensure consistent granule size, is blended with the chocolate liquor to form what's called a chocolate crumb. Depending on the recipe, milk powder, vanilla, lecithin, and other ingredients may also be added at this stage. These additions are carefully weighed and dosed using automated batching systems, which ensure that every batch conforms to a master formulation. After refining, the chocolate mass still feels dry and powdery. To turn it into a cohesive, pourable liquid with a smooth finish and stable flavor, it must undergo conching, a prolonged mixing and aeration process that can last anywhere from several hours to multiple days. Conching takes place in large heated vessels fitted with rotary arms or heavy granite rollers. The goal of conching is threefold: to develop flavor by oxidizing volatile acids, to smooth texture by distributing fat uniformly, and to improve viscosity by reducing moisture and undesirable compounds. The conching process is controlled in phases: dry conching, where the paste is crumbly and thick; plastic conching, where it softens and flows; and liquid conching, where the mass becomes fully fluid. Each conching profile is custom tailored to the specific chocolate type being produced. Milk chocolate, for instance, requires longer conching to balance milk solids and sugars, while high percentage dark chocolate may be conched shorter to retain more of its natural acidity and origin flavor. Throughout conching, temperature, shear force, and oxygen flow are all regulated. Some factories utilize closed-loop conches with nitrogen blanketing to reduce oxidation, while others incorporate vacuum systems to pull out undesirable volatile compounds. This stage is monitored using inline viscometers and gas sensors, ensuring consistent output from batch to batch. At this point in the process, the chocolate mixture has reached a smooth, glossy, and richly aromatic state. It flows as a thick liquid, its flavors matured and balanced from hours of careful mixing, grinding, and aeration. The next phase transforms that liquid mass into a finished, stable form suitable for packaging and distribution. This involves cooling and crystallizing the cocoa butter within the mixture in a very specific way, a stage that requires precision and control over time, temperature, and movement. The goal here is to encourage the formation of the right type of crystal structure in the cocoa butter. Cocoa butter can solidify into several different crystalline forms, but only one of them results in a final product that has a smooth surface, sharp snap, resistance to melting in the hand, and a stable shelf life. To achieve this, the entire mass must be carefully tempered. Tempering is carried out in machines built for continuous flow and temperature control. These tempering units begin by first heating the mixture slightly above the melting point of all crystal forms, typically around 45 degrees Celsius. This ensures that any existing crystal structures are completely melted away. The liquid is then cooled gradually, usually to somewhere between 26 degrees Celsius and 28 degrees Celsius, depending on the specific type being produced. During this cooling, movement is maintained through stirring blades and flow channels, allowing the desired type of stable crystal to begin forming. Once enough of these seeds have developed, the mixture is gently reheated to a precise finishing temperature, usually just under 32 degrees Celsius. This final temperature is critical. It allows the seeded crystals to remain while eliminating the unstable forms that would cause bloom or textural issues later on. The flow, agitation, and temperature must be maintained within a very tight range. Modern tempering equipment uses inline sensors and feedback control loops to monitor these values in real time, ensuring the product is correctly tempered before it moves into the next station. From here, the tempered liquid is conveyed to the molding lines. These are high-speed, fully automated systems designed to pour precise volumes into molds of various sizes and shapes. The molds themselves are preheated slightly to prevent premature setting and ensure even flow. As the mixture is deposited into each cavity, vibratory tables shake the molds to remove any trapped air bubbles and ensure a perfectly even distribution. Once filled and vibrated, the molds are sent through long cooling tunnels. These enclosed, refrigerated belt systems gradually reduce the temperature in controlled stages, allowing the internal structure to set without cracking or warping. The airflow, tunnel speed, and humidity are all precisely calibrated to avoid moisture condensation on the surface, which could lead to dull or sticky finishes. Once cooled and fully solidified, the bars or shapes are released from the molds using a combination of mechanical pushes and short bursts of air. The finished items are then transferred onto conveyors that lead to the inspection zone. Here, vision systems scan each piece for defects, looking for uneven surfaces, cracks, color inconsistency, or any signs of bloom. Imperfect units are automatically ejected from the line for recycling. In many operations, these rejected items are remelted and retempered to be used again in the next batch. From this point, the finished product moves toward wrapping and packaging. The type of packaging depends on the product format, whether individual bars, boxed assortments, filled shapes, or bulk items for further processing. For single bars, wrapping lines are designed to handle high volumes per minute. Each bar is conveyed through a wrapping machine that cuts, folds, and heat seals the wrapper with high-speed precision. These machines are synchronized with the flow of the production line to prevent jamming, tearing, or misalignment. Packaging materials include metallized films, waxed paper, biodegradable foils, or composite laminates. These materials are selected based on the storage requirements of the product, the region's environmental regulations, and the shelf life goals. Many manufacturers also include oxygen scavengers or modified atmosphere sealing to enhance freshness, especially for filled products. After wrapping, individual bars or pieces are grouped into larger cartons or boxes by pick-and-place robotics. These machines identify product orientation, pick them up using suction or mechanical fingers, and place them into retail boxes, display trays, or bulk cases. The outer cartons are sealed, labeled, and pass through final quality control scanners that confirm weight, barcode accuracy, and expiration coding. Palletizing comes next. Stacked and secured cartons are placed onto shipping pallets according to loading patterns that maximize space efficiency and minimize stress on the bottom layers. Pallets are shrink wrapped using rotating arms or heat tunnels and then labeled with shipping codes, batch numbers, and destination data. The entire production record for each batch is digitally logged in the factory's quality control database. This includes source information for the raw ingredients, roasting and grinding parameters, conching durations, tempering temperatures, molding timestamps, and final inspection results. Should any issue arise downstream in distribution or retail, the system allows full traceability back to the moment each unit was created. Finished pallets are moved to climate-controlled storage zones. These warehouse areas are kept at stable temperatures, generally between 16 degrees Celsius and 20 degrees Celsius, to prevent melting, blooming, or flavor degradation. Humidity is also controlled, often under 60%, to protect the product and packaging integrity. Some products are stored under specific lighting conditions to prevent discoloration, particularly white and milk varieties that are more sensitive to UV exposure. Finally, shipments are released according to production schedules aligned with distribution needs. Orders are grouped by destination region, retailer, or distributor and loaded into trucks, shipping containers, or cargo planes. Temperature data loggers may be placed inside shipments to confirm that climate conditions remain within acceptable limits throughout transport. Though the product has now left the facility, its connection to the factory process is never lost. Retail complaints, test results, or customer feedback can all be traced back to the specific day, shift, and equipment used. Manufacturers regularly run shelf life simulations, flavor degradation tests, and mechanical stress analyses on packaged goods to validate the effectiveness of the process long after the final product leaves the line. Every stage, from raw bean to packaged bar, is designed not just for efficiency, but for repeatability and control. Factories producing chocolate operate like laboratories with strict protocols, while still honoring the craft behind each ingredient's transformation. This combination of technical discipline and sensory artistry is what makes industrial chocolate manufacturing one of the most exacting and fascinating operations in the global food industry. Once the finished chocolate leaves the factory, perfectly tempered, molded, cooled, and sealed in its final packaging, the industrial process doesn't come to a halt. A crucial final phase still unfolds, one that ensures the product not only reaches shelves in perfect condition, but also maintains its quality and integrity through transportation, storage, retail display, and eventual consumption. This extended phase is managed through sophisticated logistics, environmental monitoring, supply chain coordination, and continuous quality assurance practices. While this may seem like the back end of production, It is deeply integrated into how chocolate is made and maintained on a global scale. Immediately after production, the packaged chocolate is transferred into climate-controlled storage areas within the factory's distribution wing. These areas are tightly regulated to prevent degradation. The ideal temperature for storing finished chocolate is generally between 16 degrees Celsius and 20 degrees Celsius, with humidity kept below 60%. Above this humidity threshold, there is risk of sugar bloom, a white, dusty coating that forms when moisture causes sugar to dissolve and then recrystallize on the surface. Below this range, especially in dry climates, static electricity and brittleness can become issues, particularly for filled or aerated varieties. Storage racks are arranged to allow airflow between pallets. Each pallet is tagged with a unique identifier and scanned into the warehouse management system. This allows the system to track not only where each batch is physically stored, but also how long it's been in inventory, where it needs to go next, and whether it's awaiting any last-minute quality hold releases. Before a batch can ship, a final set of post-production tests is sometimes performed on a sample group. These tests may include accelerated shelf life simulations, where chocolate is exposed to varying environmental conditions in climate chambers to determine how it performs over time. Texture analyzers may test for brittleness or softening, while gas chromatography may be used to check whether volatile flavor compounds remain stable. Once cleared, shipments are scheduled for distribution, whether headed to a supermarket distribution center, a specialty retailer, or international export. The chocolate must be loaded into transport systems that preserve the exacting conditions it was stored under. This can involve refrigerated or climate-controlled trailers, especially for higher-end varieties or filled products that are more vulnerable to heat. During warmer seasons, some companies delay shipments until nightfall or equip their pallets with insulation wraps to preserve temperature during brief exposure windows. Transport vehicles are often equipped with onboard temperature loggers. These small, battery-powered devices record environmental conditions every few minutes and are reviewed upon delivery to confirm that there were no unacceptable spikes in heat or humidity. If the data shows a breach, the receiving party may reject the shipment, even if the exterior packaging appears untouched. This level of accountability ensures that the integrity of the product is never assumed, but always confirmed. At the retailer level, chocolate continues to face environmental risks. Supermarkets and convenience stores may place chocolate in non-refrigerated aisles where exposure to lighting, fluctuating temperatures, and air conditioning vents can impact quality. To mitigate this, factory teams sometimes conduct in-store audits, either directly or through contracted merchandising specialists. These audits include checks on product placement, shelf temperature, rotation practices, and visible quality. Manufacturers also perform pull tests, where random samples are purchased directly from stores and sent back to internal labs for analysis. This helps determine if the product maintains its texture, snap, and flavor after weeks or months in the distribution system. These real-world results are fed back into the production process, helping engineers refine shelf life goals, tweak packaging barrier specifications, or adjust emulsifier ratios for better thermal resilience. Despite this rigorous system, the industrial process isn't rigid. Many manufacturers now build flexibility into their operations to support seasonal releases, new flavor experiments, and evolving consumer preferences. This includes small batch production lines within large factories that can produce limited runs of new recipes without interrupting mass-scale output. Even with these small lines, all the same steps: roasting, refining, conching, tempering, molding, wrapping are followed precisely, but in more agile formats. The long arc of chocolate production, from tropical farm to factory and beyond, is a story of transformation, precision, and protection. Each stage is critical, from developing flavor precursors during fermentation to unlocking complexity through roasting, to achieving that final, glossy finish through proper tempering and cooling. It's not just about creating a product, it's about preserving it, tracking it, testing it, and delivering it across continents in exactly the state it was intended. Firstly, that beast machine steps into the fields and starts shaking, loosening the peanuts from the roots and turning them inside out. After the plants are dug up, they're left to dry in the sun for a few days. Now the excess moisture is removed from the peanuts, and they are ready to be picked up. Here come those bulky mechanical friends to do this job. Way much easier than it seems. It picks up the dried plants, separates the peanuts from other debris, and collects them in a hopper. From the last decade, China has been the largest producer of peanuts, and this strategic country usually makes a final count of around 20 million tons of peanuts every year. We have arrived at the facility where the entire peanut pile is fed into the cleaning setup. The unwanted stuff, like stones, twigs, and other foreign materials, is removed through pre-screening. This deshelling process is most satisfying when the machines delicately remove the outer shells of peanuts and reveal that beautiful, potential, and healthy nut we all were waiting for. Hang in there for a moment. They need to inspect manually for a quality check before they send the peanuts towards seed coating removing machines. Here, with gentle shaking, a lot of air pressure, and proper programming, that brownish skin is removed from the peanuts. The peanuts are treated with a medium boiling process to lock their texture and flavor and sanitize them by killing off any harmful bacteria or microorganisms by keeping the approximate boiling temperature near 121 stacking Quicks. However, it varies from company to company. As soon as the hopper is filled with the boiled peanuts, they are immediately packed and sealed in cans for distribution. These roasted peanuts are going to transform into something super buttery and delicious. Following a little roasting, the peanuts are cooled down to reach a temperature that is safe for handling and prevents them from becoming too hot or soggy during grinding. Those chosen peanuts take a trip towards this grinder and start revealing the smooth, buttery paste we all crave. It keeps grinding the peanuts until it reaches the desired smoothness, and the magic ingredients that will enhance the flavor keep being added little by little. This whirlwind of crushing and blending turns those nuts into pure deliciousness until it's homogenization. This step is chaos that gives way to harmony. Through higher pressure, the peanut butter gains its final and smooth texture. Witness this final stage where the bottles are getting filled and sealed to secure the fresh peanut butter inside. Automated machines, like filling and cap sealing machines, work tirelessly, ensuring each jar is brimming with creamy goodness. Each jar gets dressed up, ready to impress on the supermarket shelf. Whether spread on toast, topped over ice cream, or simply enjoyed with a spoonful, chocolate peanut butter never fails to delight the senses. Chocolate peanut butter serves the taste buds with its rich, creamy texture and harmonious blend of sweet and nutty flavors. Look at those different patterns those machines are creating to give us that satisfying sight. It's more like a powerhouse of protein and other essentials for muscle repair and growth. It's delicious and satisfies your hunger between meals. Those roasted peanuts are ready for a delicious chocolate coating. This chocolate coating process requires precision to ensure each peanut is evenly coated. After coating, the peanuts are left to cool and harden. Once cooled, they are carefully packaged into food-grade safe containers for distribution and sale. Have you ever tried these? Honestly, I never have. If we talk about those chilled, delightful ice creams, you all know it's pretty popular around the globe. Every day in the United States, people consume around 50 million ice cream pints. That's enough to fill more than 9 Olympic-sized swimming pools. Whether it's a hot summer day or a chilly winter evening, Americans' love for this sweet treat stays strong all year round. And why wouldn't it? Just look at how creamy, rich, and delightful they are. Have you ever tried these Taiwanese crackers? They are pretty familiar and loved by many, from adults to children. In addition to their delicious taste and texture, Taiwanese crackers are also celebrated for their simplicity. Made from basic ingredients, they create a magical burst of flavors inside your mouth. Their straightforward approach allows the natural flavors to shine through, resulting in an authentic and satisfying snacking experience. These snacks come in a range of textures, from crispy and airy to dense and crunchy. In the last few years, there have been several conspiracies about their oil spraying, but I don't think it is a problem. Because if you dig deeper, snacking as a whole would be considered unhealthy. But after much time, a little snacking won't hurt. Do you agree? No doubt at least their production is pretty satisfying to watch. Check out the magical power of these automated systems for juice-filling sectors, where every drop counts, reducing electricity consumption. You will barely see more than a few workers working around because of the efficient automation. Talking about these bulky productions is my love language. I always fall for them. Do you? If it's a yes, we are the same, bro. So cheers to that. I want you to comment down below and let us all know whether you prefer bottled or fresh juices and why that is. Think you had a hard time scooping out the sweet and juicy flesh from the pineapple shell? I ruined 4 large pineapples just to bring out a nice pineapple ring. Didn't waste the rest though. Surprisingly, burger meat patties are low in carbs. A beef patty typically has none unless extras are added. These delicious burger patties are full of energy and nutrients, perfect for fueling your day in the most appealing ways you have ever imagined. Dried apricots are far healthier, sweet-dried fruits that can be enjoyed on their own as a satisfying snack or added to various dishes like salads, oatmeal, trail mix, or baked goods for a natural sweetness and nutritional boost. However, it's important to consume dried apricots in moderation due to their concentrated sugar content. Strawberries are delicious, sweet, and one of the most consumed fruits worldwide. But the question is, how can we have them fresh throughout the year? It has become more convenient since companies launched canned foods. This way, we can enjoy fresh strawberries all year round, even when they are not in season. Popping open a can and getting a burst of summer in every bite, either to top on your morning yogurt or blend into a smoothie, these beautiful fruits give you a lovely vibe. Honestly, these chickens are far more taken care of here, secure and cleaned, than in other local farms. Even in those large poultry facilities, they keep an eye on every chicken using robotic scanners, so they know every chicken is healthy, happy, and playing in advanced barns. Plus, did you notice those eggs systematically laying on the front row? That's how their automation works. It's all being observed and monitored until the eggs safely reach these units, where they will be tested for quality, etc. Here, the eggs automatically arrange for several inspections, like leak detection and cleaning purposes. Now comes this major egg inspector, which will approve only good eggs before they go into the disinfection chamber to remove any microorganisms or pathogens. And lastly, they are ready to come your way. No matter how some people oppose the idea of bottled juices, soft drinks, or any other processed liquids having a limited time at breakfast, I fall for those bottled and tasty juices every time. We all know it's not a healthy activity. I mean, it hardly takes 10 to 15 minutes to extract fresh juice. Anyway, that's not just my problem. the majority of us choose convenience. I'm glad we made it out successfully, most importantly, together. And please take good care of yourselves. You are precious. If we need to make that yummiest jam, we probably should focus on the healthy growth of the fruits too. Now this matter is being set under a strict guide. But yeah, giving those pots the healthier and fluffy mud with the precise amount of materials. Now these robots start at the bottom by planting strawberry plants in containers or pouches. Water is essential, so they water each pot carefully to keep the strawberries happy and hydrated. When the strawberries grow big and red, it's time to pick them. For this purpose, this gigantic robot activates its clutches to delicately pick the ripened strawberries only. Since they're on different levels, it's easy to reach and pluck the delicious berries. This entire automation is so beautiful and satisfying. How these robots peculiarly pick up the strawberry from the stem and cut it without harming it. In botanical terms, berries have their seeds inside the flesh, but strawberry seeds are on the outside, so they didn't consider it in the berry list. Those fresh strawberries have arrived at their final destination, and here they will get even royal treatment. Just a little stop for a weight check. Once they make sure the demanded number of strawberries has arrived, they take them to the sorting units. And you better know what's going to be here with them. Of course, keeping you in mind, they're going to take that stack of strawberries for a manual check and make sure that only good quality strawberries are going further. Once they're sure of that, they let them pass on until they reach safe hands. Yep, these people are going to place each strawberry in that mold for the game-changing results. These robots automatically detect the green hull of a strawberry and beautifully just remove it without harming any other inch of the fruit. This is mind-blowing. Everything is under mechanical control. You can see how sharp eyes they have. Come on, they're doing this for you. Strawberries grow close to the ground, making them more susceptible to dirt, sand, and even tiny insects. The first wash, often a combination of water and little vibrations, removes these surface impurities. That's very important. But you know, fruits and veggies like these need another bath too. That's why they're given a second wash, often involving specialized sprays or misting with solutions like chlorine dioxide, which takes care of the tougher particles like pesticide residues and bacteria. This double trouble approach ensures the strawberries are as clean and safe as possible. They care about you. We care about you. See how honored we are to have you, just like these red, juicy strawberries. These fresh strawberries are now put into these containers. Yep, that's how you get the true and fresh flavor of frozen strawberries, because they are the same as, what to say, straight from farms to your plate. They are packed and firmly sealed to lock the pulpy fruit inside the food-grade containers. Just check out that large number of cans. Secondly, they use some of the frozen strawberries to make that glittery, yummy strawberry jam. All these frozen berries are put into the carriers to take them to the next stop, which is to load them into a container to add further ingredients. As the strawberries are loaded, now it's time to add further ingredients like sugar. They make sure the jam looks good, tastes good, and has the perfect texture. Once the handsome amount of sugar is poured, they need to control those figures and machines' capabilities by playing with some important buttons. The hot water tub is ready for these beautiful entities to enter and get bathed in the sweet syrup. What are they peeking at? Okay, the real drama has just begun. Once all the pulp comes to mix in that syrup, they put that material through sieves. This is important to give you that pulpless, smooth, jiggly jelly jam. Mixing mixing, and more mixing. Everything is heated up in big pots or machines to make the strawberries blend and taste awesome. A special thing called pectin is added to make the jam just the right thickness. It's time to cook the material until it reaches its perfect texture, and that desired texture can be seen here. I think it's done. Yep, he's going to test the jam base to see if it's ready or needs to be cooked more. And yeah, it's good to go. Now the final process begins, to churn the mixture, to add a little more smoothness and to cool it side by side. A little now, it's like letting the flavors and texture settle and become best friends before they get packed into jars. And just wait. Here we go. The whole warm jam base is ready. More close up here. It is, that creamy, smooth flow of my favorite jam. It's driving me crazy. Okay, time to pour that base and lock it in the jars. For that, these empty and starving bottles arrive. They are first neatly organized properly. The jam is carefully poured into jars all by itself. This process is usually automated in factories, with machines making sure each jar gets the right amount of fruity goodness. Here, we reach their sealing stage, where lots of lids are first picked in a proper style, beautifully conveyed to the roller coaster sort of belt, and finally to the sealing section where machines tightly seal the jars with lids. Okay, all those bottles are washed after being tightly sealed so that whatever sweetness remains on the outer side of the jars will be bathed away. We're now in the sticker section, where the robots will conveniently wrap stickers around these bottles so you will easily identify it's factory sealed. And of course, read that chart before eating anything. It's a good habit though. If you do, well, I don't. There's another technique too to add the labels one by one. All the bottles are labeled from whatever company they belong to and then piled up in the containers for the final bulk packaging. Bye-bye jam bottles. Don't forget my address and reach me soon. These mini jam bottles are filled up with the same freshness of fruit pulp and flavor to enrich your taste buds. Are those little nasty jam packets? You know, the ones at restaurants tucked next to the bread basket, bursting with fruity sunshine in one tiny bite. They're more than just sugar bombs. They might be tiny, but they're full of flavors to serve as starters for every meal. Also, these bite-sized marbles help stop food waste and make sure every spoonful is just right. These machines are the backbone of many industries, from food production to textile manufacturing to construction. With their robust blades and precise cutting mechanisms, they're built to tackle even the toughest materials. Imagine a scene where smoky aromas fill the air as meat sizzles on the grill, tantalizing taste buds with every flip and sear. Curious about the staggering output of flatbread producing machines in a single day? Prepare to be amazed. These efficient marvels can churn out an impressive number of flatbreads thanks to their high-speed capabilities and precision engineering. Depending on the size and capacity of the machine, production numbers can vary widely, ranging from thousands to even tens of thousands of flatbreads per day. Crafted with the finest ingredients and expert techniques, our pastries are a symphony of flavors and textures. Meet chocolate depositors, the sweet secret behind every delectable treat. Hazelnuts are packed with nutrients like protein, healthy fats, fiber, and various vitamins and minerals. Not only do they promote heart health and aid in weight management, but they also support brain function and contribute to healthy skin and hair. These little blue gems are packed with antioxidants, which help fight off harmful molecules in our bodies and keep us feeling great. Motivate us to create more satisfying videos like these and smash the like button. These factories aren't just about quantity, they're about crafting quality too, ensuring that each slice of salami delivers a burst of savory perfection. Removing the skin helps trim down on excess fat and calories. You see, much of the fat in chicken resides in the skin. So by peeling it off, you're opting for a leaner, healthier option. Additionally, without the skin acting as a barrier, marinades and seasonings can penetrate the meat more effectively, enhancing flavor throughout. Talking about almonds, you must eat them daily so you can remember us and keep watching our videos. Cheese holds a special place on plates globally, with millions indulging in its creamy goodness daily. Hey, if you're enjoying this video, make sure you hit that like button so we'll know how many people are interested in watching our upcoming videos. The ancient Egyptians were one of the first civilizations to enjoy sweets, using honey as a primary sweetener. That minced meat, also known as ground meat, is incredibly versatile and used in a wide array of dishes worldwide. From savory meatballs to juicy burgers, its adaptability knows no bounds. It all boils down to freshness and food safety. Ideally, you want to consume tray-sealed meat within a few days of purchase to ensure peak freshness and flavor. Let's crunch into the world of factory-made delicious potato chips. From sourcing the finest potatoes to adhering to strict quality control standards, these factories ensure that each chip meets the crispy, satisfying standard you expect. These machines are the backbone of large-scale food operations, capable of handling a wide variety of produce with speed and accuracy. These factory-prepared meals undergo stringent quality control measures to ensure they meet safety and nutritional standards. From automated sorting systems that ensure only the highest quality ingredients make it onto the production line to state-of-the-art packaging machines that swiftly seal products for freshness, these machines are essential for meeting consumer demand while maintaining high standards. Each pepper is carefully inspected for size, color, and quality, ensuring only the best make it to market. Each juicy bite is a refreshing explosion of tangy sweet goodness, leaving taste buds dancing with delight. These innovative contraptions are designed to streamline the process of pouring batter with precision and consistency. These machines are the masters of precision, effortlessly dispensing just the right amount of batter, dough, or filling with each press of a button. That's where the multi-head weighing machine shines. Its multiple weigh heads work simultaneously to ensure accuracy and efficiency. Imagine effortlessly removing the outer layer of fruits and vegetables with precision and finesse. That's the magic of these machines. From potatoes to oranges, they strip away the tedious task of manual peeling, saving you time and labor costs. But it's not just about convenience, it's about consistency. With peeling machines, you get uniform results every time, ensuring your products look as good as they taste. Wait. Before watching this clip, were you thinking peeling fruit is the hardest thing to do? I mean, it's messy, but not anymore. It's not just about indulgence, there are benefits too. Chocolate breads pack a double punch of flavor and nutrition. Bursting with tropical flavor and juiciness, mangoes are nature's candy that never disappoints. From automated temperature control to efficient oil filtration systems, they're designed to optimize performance and minimize waste.